Hello there and welcome to Life Beyond Seen, where curiosity settles in quietly and science moves at an unhurried pace. Tonight we're turning our attention towards something that covers most of our world, touches every coastline, shapes every climate, and still manages to remain largely out of reach. We're talking about the ocean, not just the waves you see from the shore, not just the beaches and coral reefs that appear in travel photos, but the entire body of salt water that wraps around this planet like a continuous shifting skin. When you picture Earth from space, you see blue, vast stretches of it. More than 70% of the surface is ocean. It dominates the globe so completely that calling our home Earth almost feels misleading. Ocean would be more accurate. And yet, despite living on what is essentially a water world, we have explored only a small fraction of it in any direct, detailed way. That raises a question worth sitting with for a moment. When you think of exploration, what comes to mind? Rockets leaving the atmosphere, astronauts floating in orbit, rovers crawling across dusty Martian plains. Space feels distant and dramatic, and we often talk about it as the final frontier. But what if the largest frontier isn't above us at all? What if it's below? Before we lower ourselves into that thought, I'm curious. Where are you listening from tonight? Are you near a coastline, where the tide rises and falls outside your window? Or are you inland, far from salt water, perhaps only encountering the ocean through documentaries and maps? And what time is it where you are right now? Early evening with a dim sky, or late enough that the world outside has quieted down? It's interesting, isn't it, that no matter where we are, the ocean is influencing us. The air you're breathing carries moisture that may have evaporated from it. The temperature around you is moderated by it. The weather patterns that passed over your city were shaped by it. Even if you can't see it, the ocean is involved. If you find this kind of slow exploration calming or thought-provoking, feel free to like the video or subscribe. It helps this space reach others who might enjoy a gentle dive into questions that don't demand urgency. There's no rush here. We're simply looking a little closer at something that has always been present. So let's begin with the scale of the claim. You've probably heard the statistic before. Humans have explored more of the surface of the moon than the depths of our own ocean. That line gets repeated often, sometimes with dramatic flair. It sounds surprising, maybe even slightly embarrassing, but how true is it? To answer that, we first need to be clear about what explored really means. Does it mean visited by a human being? Does it mean photographed, mapped, sampled, measured? Because depending on the definition, the percentage changes. If we're talking about detailed high-resolution mapping of the ocean floor, the number is small. Only a modest portion of the seabed has been mapped in the kind of resolution that allows scientists to see individual features clearly. Large areas have been scanned using sonar from ships or satellites, but those scans often produce rough outlines rather than fine detail. Imagine looking at a mountain range through a fogged window. You can tell there are peaks and valleys, but you can't see the cracks in the rock. If we're talking about direct human visits to the deep ocean, the number becomes even smaller. Only a handful of people have descended to the deepest known point in the ocean, the Challenger Deep in the Mariana Trench. Meanwhile, dozens of astronauts have walked on the moon, and hundreds have travelled to space. It sounds dramatic, but there's a reason for it that doesn't rely on mystery or neglect. The ocean is difficult to reach in a very specific way. The deeper you go, the more pressure builds above you. Water is heavy. Every 10 meters of depth adds roughly 1 atmosphere of pressure. By the time you reach the deepest trenches, the pressure is more than 1,000 times what you experience at sea level. That's enough to crush unprotected equipment instantly. So while space may be cold, airless, and filled with radiation, the deep ocean presents its own set of challenges. You're not simply floating in emptiness. You are surrounded on all sides by immense weight. Every vehicle that descends must be engineered to withstand that pressure without failing. A single structural weakness can become catastrophic, and yet, despite the difficulty, we have tried. Humans have always been drawn to the water. Early civilizations learned to cross it in boats carved from wood or stitched together from reeds. They charted coastlines, named currents, and followed the stars across open sea. For thousands of years, exploration meant horizontal movement across the surface. The idea of going down came much later. For most of history, the deep ocean was a place of speculation. Sailors imagined enormous creatures living below. Maps included sea serpents and warnings about unknown depths. Even scientists in the 18th and 19th centuries believed that life might not exist beyond a certain depth. The pressure, the darkness, the cold seemed too extreme. That assumption changed in the late 19th century during expeditions like the voyage of the HMS Challenger. For the first time, systematic measurements of ocean depth were taken across wide regions. Samples were brought up from the seabed. Life was discovered in places where it was thought impossible. The deep ocean was not empty, it was inhabited. Still, even those early expeditions barely scratched the surface. Measuring depth with weighted lines gave a number, but it did not reveal what lay between the surface and the bottom. It did not show the landscapes hidden in darkness. Fast forward to the 20th century and technology began to shift the balance. Sonar allowed ships to send sound waves downward and measure how long they took to bounce back. That simple idea transformed our understanding of the seafloor. Suddenly, mountain ranges were discovered underwater, trenches deeper than any canyon on land, vast plains stretching for thousands of kilometers. The discovery of the mid-Atlantic ridge revealed that the ocean floor itself was dynamic. Tectonic plates were spreading apart, creating new crust. The seafloor was not static. It was constantly changing, though at a pace too slow to notice without instruments. Yet even with sonar, much of the mapping has been low resolution. Satellite altimetry can infer large features by measuring slight changes in sea surface height, caused by gravity differences from underwater mountains or trenches. It's a clever method, but it's indirect. It gives shape without texture. Imagine trying to understand an entire continent using only blurry satellite images. You would see the outline, the general terrain, maybe the largest rivers. But you would miss the forests, the roads, the individual buildings. That's roughly the level of detail we have for large portions of the ocean floor. And then there's the water column itself, the vast space between the surface and the seabed. It is easy to think of it as empty, but it is not. Layers exist based on light penetration. The upper zone, where sunlight reaches, supports photosynthesis. Below that lies the twilight zone, where light fades. Deeper still is complete darkness. Each of these zones contains life adapted to its conditions. Some organisms generate their own light through bioluminescence. Others drift for miles without ever encountering solid ground. The ocean is not just a surface and a floor. It is a three-dimensional environment that extends downward for kilometers. When we say we have explored only a small percentage of the ocean, we are often referring to detailed observation. We have sampled water from many locations. We have measured temperature, salinity, and currents. We have identified major ecosystems. But direct close-up exploration using submersibles or remotely operated vehicles has covered only limited regions. Even today, a large portion of the deep sea has never been visited by a camera. Entire mountain ranges, trenches, and plains remain unseen by human eyes or lenses. We know they exist because of sonar. We know their approximate shape. But no one has descended to document them directly. There is something striking about that. On a planet where satellites can zoom in on individual city blocks, there are landscapes larger than entire countries that have never been photographed up close. At the same time, it's important not to frame this as ignorance in every sense. Scientists do understand many of the ocean's large-scale processes. Currents like the Gulf Stream are well studied. The role of the ocean in absorbing carbon dioxide and regulating climate is measured carefully. Fisheries are monitored. Coastal ecosystems are mapped in detail. The unexplored percentage refers mostly to the deep ocean floor and certain remote regions. Coastal waters, which are economically and ecologically significant, are comparatively well studied. The deeper you go and the farther from shore, the thinner our direct knowledge becomes. This creates an interesting contrast. We rely on the ocean heavily. It provides food for billions of people. It transports goods across continents. It influences rainfall patterns and global temperatures. Yet beneath a certain depth, it becomes a place we understand mostly through instruments rather than presence. And presence matters. There is a difference between knowing that a mountain exists and standing at its base. There is a difference between measuring pressure at 5,000 meters and watching a creature move in that environment. You might be wondering why we've invested more effort in space than in the deep ocean. The reasons are practical and cultural. Space exploration has been driven by competition, prestige, and the desire to push technological boundaries. It captures public imagination in a way that slow, dark descents often do not. The deep sea does not offer dramatic launch sequences or visible horizons. Its challenges are hidden from view. Funding often follows attention, and attention gravitates toward what feels new or expansive. Yet in recent years, interest in ocean exploration has been increasing. International efforts aim to map the entire seafloor in high resolution within the coming decades. Advances in autonomous underwater vehicles allow longer missions without human crews. Sensors are becoming smaller and more efficient. As we continue, we'll look more closely at how much of the ocean has been mapped precisely, how exploration actually works, and what remains unseen. Because while the phrase, "we've explored less than 5%, gets repeated often, the reality behind it is more nuanced and more interesting. Before diving deeper into statistics and methods, it helps to pause and consider something simple. When you stand at the edge of the sea and look out, what you're seeing is a surface that hides an entire world beneath it. That world is not uniform. It includes trenches deeper than Mount Everest is tall. It includes volcanic ridges that encircle the globe. It includes ecosystems that do not depend on sunlight at all. And most of that world remains largely unvisited. From here, it becomes useful to ask not just how much we've explored, but how we measure exploration in the first place. Because a blurry map is not the same as a detailed survey, and a sonar outline is not the same as a camera descending slowly into darkness. The numbers tell one story, but the methods behind them tell another, and that's where the real picture begins to take shape. When you look at Earth from space, it appears overwhelmingly blue. Oceans stretch across the globe in a continuous sweep, broken only by the irregular shapes of continents and islands. From that vantage point, the planet seems familiar, almost fully revealed. The oceans are right there in plain sight, dominating the surface. It gives the impression of completeness, as if the water has already been accounted for simply because we can see it. But that impression is misleading. The blue we see from space is only the uppermost skin of something far more complex. It is a surface layer reflecting sunlight back toward the cameras of satellites and spacecraft. It tells us almost nothing about what lies below. And yet, psychologically, it creates a sense of familiarity. If something is visible, we assume it is known. This is where the illusion begins. We often refer to Earth as the blue planet, and the name feels accurate. About 71% of the planet's surface is covered by ocean. That statistic is widely repeated, and it is correct. But surface coverage is not the same as understanding. If someone handed you a globe painted entirely blue, you would know that water dominates the planet. What you would not know is how deep it is, how it moves, what lives within it, or what structures lie beneath. There is a subtle mental shortcut at work. When we see something frequently, we assume it is well understood. The ocean is in documentaries, in weather reports, in shipping routes, in holiday photos. It feels present and integrated into daily life. But most of those references concern the uppermost layer, the thin zone where sunlight penetrates and ships travel. Below that lies a vertical dimension that is easy to forget. The average depth of the ocean is about 3,700 meters. In some places it plunges to nearly 11,000 meters. If you were to remove all the water from the oceans, the exposed terrain would reveal mountain ranges longer than the Andes, trenches deeper than the Grand Canyon, and plains wider than entire countries. Yet because all of it sits underwater, it does not occupy our mental map in the same way land does. We are creatures adapted to land. Our senses evolved to function in air, under gravity that pulls us towards solid ground. We see horizons, hills, forests. Water, by contrast, obscures vision. Light fades quickly as depth increases. Sound travels differently. Movement is slower and requires buoyancy or propulsion. For most of human history, the ocean's interior has been physically inaccessible. This physical separation reinforces the illusion. Because we cannot easily enter the deep ocean, we rarely think about it in detail. The surface becomes a stand-in for the whole. When a satellite image shows swirling currents or hurricanes forming over open water, it feels comprehensive. The entire ocean appears accounted for within that frame, but satellites primarily observe the surface. They measure sea surface temperature, wave height, chlorophyll concentrations in the upper layers. They can infer certain things about what lies below based on subtle gravitational effects or thermal patterns, but they do not directly see into the depths. Imagine standing over a lake on a calm day. The surface is smooth, reflective. You can see the sky mirrored back at you. Without tools, you would have no idea whether the lake is 2 meters deep or 200. You would not know if the bottom is flat or full of ridges. From above, it is just a surface. Scale that up to the size of the Earth's oceans, and the challenge becomes clear. There is another factor that contributes to the illusion of familiarity: mapping. We often say the world has been mapped, and in a sense, it has. We have global maps that show continents, coastlines, and ocean basins, but much of the detailed mapping of the seafloor has been indirect and low resolution. Large swathes of the ocean floor have been mapped using satellite altimetry, which detects tiny variations in sea surface height caused by gravitational differences from underwater features. This technique is impressive. It allows scientists to infer the presence of seamounts, ridges, and trenches, but it produces a blurred outline rather than a sharp image. It is comparable to looking at a landscape through thick mist. You see shapes, not textures. Only a smaller percentage of the seafloor has been mapped using ship-based sonar at high resolution. These detailed surveys require vessels to travel back and forth across specific areas, sending sound pulses downward and measuring the return time. It is a slow and expensive process. Given the vastness of the oceans, completing such surveys globally is a monumental task. The numbers often quoted vary depending on the criteria used, but high-resolution mapping covers only a fraction of the total seabed. That means large underwater regions remain known only in broad outline. And then there is the matter of biological exploration. When people hear that we have explored only a small percentage of the ocean, they sometimes imagine that vast regions are completely unknown in every respect. That is not entirely accurate. Scientists have collected water samples from across the globe. They have measured currents, temperatures, salinity, and chemical composition at different depths. We understand large-scale circulation patterns, such as thermohaline circulation, which drives global ocean currents. Yet direct visual exploration of deep habitats remains limited. Many deep-sea expeditions focus on specific sites: hydrothermal vents, coral mounds, submarine canyons. These areas are chosen for scientific interest or accessibility. Between them lie immense stretches of abyssal plain that have rarely been visited by cameras. The illusion of the blue planet also extends to life itself. The ocean appears uniform in colour from space, but biologically it is highly varied. The sunlit upper layer supports phytoplankton, which form the base of marine food webs. Beneath that, in the twilight zone, organisms rely on falling organic matter from above or on predation. Deeper still, in complete darkness, life has adapted to extreme pressure and limited food supply. Hydrothermal vents, discovered in the late 20th century, revealed ecosystems based not on sunlight, but on chemosynthesis. Bacteria convert chemicals from Earth's interior into energy, supporting complex communities of tube worms, crustaceans, and fish. These discoveries reshaped our understanding of where life can exist. And yet hydrothermal vents occupy only small portions of the seafloor. There are likely many more such sites that have not been located. Each vent system discovered suggests the possibility of others hidden across vast distances. The blue planet illusion can also lead to assumptions about resource availability. Because the ocean is so large, it is often perceived as inexhaustible. Fish populations were once thought to be limitless. Waste was dumped into the sea under the assumption that it would be diluted beyond consequence. Over time, those assumptions have proven incorrect. Overfishing has depleted certain stocks. Plastic pollution accumulates in gyres. Dead zones form where nutrient runoff disrupts oxygen levels. The apparent vastness of the ocean masked its vulnerability. There is a paradox here. The ocean feels both overwhelmingly large and surprisingly fragile. Its surface area dwarfs all land combined. Yet specific ecosystems can be damaged by localized human activity. Part of the difficulty lies in perception. When you look at a forest being cleared, the change is visible. When coral reefs bleach due to warming temperatures, the change is underwater and often out of sight. The blue planet image remains visually unchanged from space, even as conditions shift below. Another layer of illusion comes from technology itself. Modern navigation systems rely on GPS satellites and precise mapping. Shipping lanes cross oceans with remarkable efficiency. Submarine cables carry data across seabeds, connecting continents. These systems give the impression of thorough integration and knowledge, but much of that infrastructure occupies specific corridors. The routes are mapped carefully, but the surrounding areas may not be. A cable laid across the ocean floor does not require detailed knowledge of every nearby ridge or trench. It requires a viable path. Similarly, oil and gas exploration in offshore regions has driven detailed surveys in certain areas. Yet those surveys are focused and limited to zones of economic interest. Beyond them lie expanses that have not been examined with the same intensity. It is also worth considering how language shapes perception. Phrases like uncharted waters evoke a bygone era of wooden ships and blank maps. Today, because no region of the ocean is entirely absent from maps, we rarely think of any part of it as uncharted. But charted in outline is not the same as understood in detail. If someone told you that a continent had been mapped only in broad strokes, with many areas seen only from high altitude and few ground surveys conducted, you would likely consider it largely unexplored. That description applies to significant portions of the deep ocean floor, and yet, because it is underwater and not directly inhabited by humans, it occupies less space in public imagination. There is also a subtle psychological factor at play. We tend to associate exploration with expansion into new territory. Space exploration fits that narrative neatly. The ocean, by contrast, surrounds us already. It feels familiar simply because it is part of our existing world. But familiarity is not the same as knowledge. Consider how many people have walked on the moon. Fewer than 24 humans have travelled there, and 12 have walked on its surface. Meanwhile, only a small number of individuals have descended to the deepest ocean trench. In both cases, the number of direct human experiences is limited. The difference lies in perception. The moon is visibly distant and alien. The ocean appears continuous with our daily environment. That visual continuity creates comfort, and comfort can reduce curiosity. Still, scientists are far from complacent. Large international initiatives aim to map the entire seafloor at higher resolution within the coming decades. Autonomous underwater vehicles can now operate for extended periods without direct human control. Advances in materials science allow deeper dives with improved safety. Each new expedition reveals species never seen before, geological formations not previously documented, and chemical processes that reshape understanding of marine systems. Estimates suggest that a significant percentage of marine species remain undescribed by science, particularly in deep environments. The illusion of the blue planet begins to fade when you look at these discoveries not as isolated events, but as evidence of how much remains. At the same time, it is important to maintain perspective. We are not completely ignorant of the ocean. We understand its major basins, its role in global climate regulation, and many of its large-scale processes. Weather forecasting relies heavily on ocean data. Climate models incorporate ocean heat content and circulation. The gap lies in fine detail, in direct observation, in the slow accumulation of knowledge from specific locations, and that gap is understandable when you consider scale. The ocean covers about 361 million square kilometres. Surveying that area in high resolution using ships that move at modest speeds takes time. Each expedition requires funding, personnel, equipment, and favourable conditions. The Blue Planet image compresses all of that into a single calm frame. It shows no indication of pressure gradients, darkness, or complexity. It presents unity where there is variation. As we move forward, it becomes useful to shift from the image of the ocean as a smooth blue surface to the idea of it as a layered, structured environment that extends downward for kilometres. The surface is merely the entry point. Understanding how much of it we have truly explored requires looking beyond that reflective skin and into the methods, the challenges, and the specific regions where knowledge thins out. Because once the illusion is set aside, the question becomes more precise, and the scale of what remains begins to feel less abstract and more concrete. Long before satellites traced coastlines with precision and digital charts guided ships across open water, the ocean was navigated through memory, observation, and cautious imagination. The first attempts to understand it did not begin with depth measurements or sonar pulses. They began with people standing at the edge of shorelines, looking outward and deciding to move forward anyway. The earliest maps of the ocean were not maps in the modern sense. They were stories. They were directions passed from one sailor to another. They were warnings about reefs, currents, and seasonal winds. Knowledge of the sea was practical and local, built from repeated journeys rather than systematic surveys. For coastal communities, the ocean was both barrier and pathway. It separated land masses, but it also connected them. Early seafarers learned to read patterns in waves and winds. They noticed how birds flew at certain times of day, how cloud formations hinted at nearby islands, how stars shifted across the sky with the seasons. Polynesian navigators, for example, crossed vast stretches of the Pacific Ocean using knowledge passed down through generations. They did not rely on compasses or written charts. Instead, they memorized star paths, wave patterns, and subtle changes in ocean swell that indicated land beyond the horizon. Their maps existed in the mind, encoded in training and tradition. In the Mediterranean, ancient civilizations such as the Phoenicians and Greeks developed trade routes that linked distant ports. Their understanding of the sea expanded gradually with each voyage. Coastlines were traced by sailing along them, islands were noted when encountered. Harbours were described in practical terms: safe anchorage, fresh water, prevailing winds. These early maps were narrow in scope. They focused on coastlines rather than open ocean. The sea itself was often depicted as blank space between land masses. It was not yet seen as a terrain worthy of mapping in its own right. Part of this was technological limitation. Without accurate instruments for measuring longitude, determining one's exact position at sea was difficult. Latitude could be estimated by the height of the sun, or stars above the horizon, but longitude required precise timekeeping that would not become reliable until the 18th century. So early maps emphasised what could be confirmed visually: the outline of coasts, the location of islands, the shape of peninsulas. The ocean interior remained undefined. There was also imagination filling the gaps. Medieval European maps sometimes included sea monsters in unexplored regions. These illustrations were not necessarily literal beliefs, but they reflected uncertainty. Where knowledge ended, speculation began. Blank spaces invited interpretation, and the ocean, vast and opaque, seemed to conceal unknown dangers. Cartographers often wrote phrases like, "Here be dragons," in areas that had not been charted. The ocean was not just unknown in a scientific sense, it was unknown in a psychological one. It represented risk. As navigation improved during the Age of Exploration, maps became more detailed. Voyages sponsored by European powers extended known coastlines across the Atlantic, around Africa, and eventually across the Pacific. Each expedition added lines to the edges of continents. Yet even as global maps of coastlines took shape, the interior of the oceans remained essentially invisible. Ships travelled across surfaces. They did not measure depth systematically. The seafloor was beyond reach. When Ferdinand Magellan's expedition circumnavigated the globe in the 16th century, it demonstrated that the oceans were connected in a continuous system. That realization was significant. It transformed the ocean from a series of separate seas into a global body of water. Still, the maps produced during that era depicted the ocean primarily as space between lands. Trade routes were drawn as lines across blue expanses, but the water itself was featureless. This perspective persisted for centuries. Even into the 18th century, most nautical charts were designed for navigation safety. They showed coastlines, shoals, reefs, and known hazards near shore. Depth measurements were taken using weighted lines dropped overboard, but these were typically limited to coastal approaches where grounding was a concern. The open ocean was considered too deep to measure effectively with available tools. Sailors knew it was deep, but how deep remained uncertain. Some speculated that the ocean might be bottomless in certain regions. In the 19th century, curiosity about the deep ocean began to shift from practical navigation to scientific inquiry. Advances in instrumentation allowed for more systematic measurement. Weighted lines were improved, and deeper soundings became possible. One of the most important turning points came with the voyage of the HMS Challenger between 1872 and 1876. This expedition is often regarded as the foundation of modern oceanography. Over nearly 4 years, the Challenger travelled around the world, taking depth measurements, collecting water samples, and dredging the seafloor. For the first time, scientists attempted to measure the ocean systematically across vast distances. They discovered that the seafloor was not uniform. It contained mountain ranges, plains, and deep trenches. Before this expedition, many scientists believed that life could not exist in the deep ocean due to pressure and darkness. Samples brought up by the Challenger proved otherwise. Organisms were found living at depths previously thought sterile. The maps that followed were still limited, but they began to show contours beneath the water. The ocean was no longer a blank blue space. It had structure. Even so, the process was slow. Each depth measurement required lowering a line, waiting for it to reach bottom, and hauling it back up. Covering large areas in this way was time-consuming. Gaps remained vast. The development of sonar in the early 20th century changed the pace of mapping dramatically. By sending sound waves downward and measuring their return time, ships could measure depth continuously while moving. This allowed for more detailed bathymetric maps. As sonar surveys accumulated, features like the Mid-Atlantic Ridge were revealed. A massive underwater mountain chain stretching thousands of kilometers was discovered running through the center of the Atlantic Ocean. This discovery played a key role in the development of plate tectonics theory. Suddenly, the seafloor was recognized as dynamic. It was not a static basin filled with water. It was an active geological landscape. And yet, even with sonar, mapping the entire ocean floor at high resolution remained challenging. Ship time was limited. Weather conditions affected surveys. The ocean's sheer size meant that even decades of effort left large regions covered only in broad strokes. It is worth considering the contrast between land and sea mapping during the same period. On land, surveyors could walk across terrain, take detailed measurements, and return repeatedly. Railroads and roads facilitated access. In the ocean, access required vessels, crews, and specialized equipment. mapping the ocean was not simply a matter of drawing lines. It required engineering solutions to reach depth safely and consistently. As the 20th century progressed, ocean mapping became increasingly important for reasons beyond curiosity. Submarine cables needed routes, naval operations required detailed charts, oil and gas exploration pushed surveys into deeper waters. These practical motivations accelerated mapping in certain regions. However, they did not result in uniform coverage. Areas of economic or strategic interest were prioritized. Remote regions often remained less detailed. Satellite technology introduced a new method for inferring seafloor features. By measuring slight changes in sea surface height caused by gravitational variations, scientists could estimate the presence of underwater mountains and trenches. This provided near-global coverage, but at relatively low resolution. It was a significant achievement. For the first time, a consistent global picture of the ocean floor existed. But like early coastline maps, it represented a first layer rather than a complete portrait. When people today hear that only a small percentage of the ocean has been explored, they may imagine entirely blank maps. That is not the case. The broad outlines are known. The major basins, ridges and trenches have been identified. What remains incomplete is the fine detail, the kind of mapping that would allow someone to navigate the seafloor as confidently as a hiker navigates a mountain trail. The first maps of the ocean were cautious sketches of coastlines. Over time, those sketches expanded into global charts. But even now, the process of drawing the ocean's full portrait continues, and as mapping technology improves, attention shifts from simply knowing where features are to understanding what they contain. Geological structure leads to biological questions. Depth contours lead to ecosystem studies. The act of drawing maps has always been more than cartography. It is an attempt to reduce uncertainty. Early sailors drew maps to survive. Modern scientists draw maps to understand processes that affect climate, biodiversity and planetary systems. Still, there is something humbling about the progression. For thousands of years, the ocean was a boundary marked by fear and speculation. Then it became a network of trade routes, then a scientific frontier. Each stage added lines and numbers, but none erased the sense of scale. Even today, if you were to look at a detailed bathymetric map of the world, you would see colours representing depth gradients and contours indicating terrain. It looks comprehensive, but in many regions those contours are based on sparse data points interpolated across wide distances. The map appears solid. The knowledge beneath it can be thin. As exploration continues, the tools change. Autonomous underwater vehicles can now travel closer to the seafloor, capturing high-resolution imagery and data. Remotely operated vehicles send back video from depths that would crush unprotected humans instantly. Each expedition refines the map slightly. Each survey adds texture. The process of drawing the ocean's map is ongoing. It began with cautious coastal sketches and has evolved into global initiatives aiming to map every square kilometre of seabed in detail. But even as lines accumulate and colours fill in, the ocean resists full disclosure. Its depth, pressure and darkness impose limits that land does not. And so, the act of mapping remains not just a technical task, but a reminder of how recently the ocean shifted from blank space to measured terrain. From here, understanding how we measure depth and what those measurements reveal becomes essential. Because drawing the first maps was only the beginning. Measuring the depth themselves would transform the ocean from surface pathway into vertical landscape, and that shift would open an entirely new dimension of exploration. For most of human history, the ocean's depth was a question rather than a number. Sailors knew it was deep because anchors disappeared below sight, and weighted ropes kept ascending long after arms grew tired. But knowing something is deep and knowing how deep are two very different things. Early attempts to measure the ocean's depth were simple and direct. A rope or line was lowered over the side of a ship with a weight attached to its end. When the weight touched bottom, the line slackened. The length of rope let out gave a rough estimate of depth. This method, known as sounding, was practical in shallow coastal waters where navigation hazards mattered most. Near shore, where ships risked running aground, sounding was essential. Sailors needed to know whether there was enough water beneath their hulls. These measurements were recorded on nautical charts, creating the first depth contours along coastlines. But as ships ventured farther offshore, sounding became less practical. Lowering a line thousands of meters required heavy equipment and significant time. The line could drift with currents, making readings inaccurate. In rough seas, maintaining vertical alignment was nearly impossible. For centuries, the open ocean remained largely unmeasured simply because the tools were insufficient. There were also misconceptions about what the measurements might reveal. Some believed the ocean might be uniformly deep, a vast basin with little variation. Others speculated that certain regions could be bottomless. Without consistent data, theories filled the gaps. In the 19th century, curiosity intensified. As undersea telegraph cables were planned to connect continents, understanding seafloor depth became more than academic. Engineers needed to know the terrain over which cables would be laid. This practical need drove improvements in sounding techniques. Weighted lines were refined. Heavier sinkers reduced drift. Mechanisms were developed to detect the moment the weight hit bottom more precisely. Specialized sounding machines allowed for deeper measurements than ever before. One significant development was the use of piano wire instead of rope. Wire was thinner and less affected by currents, allowing for more accurate deep soundings. The wire could be paid out from a drum and reeled back in mechanically, reducing physical strain on crews. Despite these improvements, measuring depth remained slow. Each reading required lowering the weight to the seabed and hauling it back up. Covering large distances required many separate measurements, spaced miles apart. The voyage of the HMS Challenger in the 1870s marked a turning point. Equipped with improved sounding equipment, the Challenger expedition systematically measured depths across the world's oceans. Over nearly 4 years, the crew took hundreds of soundings. These measurements revealed that the ocean floor was not flat. They identified deep trenches and extensive plains. The deepest point measured during that expedition was in the Western Pacific, a region later known as the Mariana Trench. The idea that the ocean had structure comparable to land was transformative. It shifted perception from the ocean as a simple container of water to a complex geological landscape. Still, even with improved sounding lines, the method was limited. It provided individual depth points rather than continuous profiles. Between each measurement lay uncertainty. The real revolution came with sound. In the early 20th century, scientists and engineers began experimenting with echo sounding. The principle was straightforward. A sound pulse is emitted downward from a ship. It travels through the water, reflects off the seabed, and returns to the ship. By measuring the time between emission and return, and knowing the speed of sound in water, depth can be calculated. Sound travels through water at roughly 1,500 meters per second, though the exact speed varies depending on temperature, salinity, and pressure. By accounting for these variables, depth measurements could be made quickly and repeatedly. Unlike weighted lines, echo sounding allowed ships to measure depth continuously while moving. Instead of isolated points, researchers could generate profiles of the seafloor beneath entire routes. This technology developed rapidly during and after World War I, partly driven by military needs such as submarine detection. After the war, it was adapted for scientific exploration. As echo sounding surveys expanded, large-scale features began to emerge clearly. The Mid-Atlantic Ridge was mapped in greater detail. Deep ocean trenches were charted with increasing accuracy. Seamounts, underwater volcanoes rising from the seafloor, were identified across multiple basins. The discovery of these features had implications beyond cartography. They contributed to the development of plate tectonics theory in the mid-20th century. The pattern of ridges and trenches suggested that the seafloor was spreading and subducting, reshaping Earth's surface over geological time. Measuring depth was no longer just about navigation or cable placement. It became central to understanding planetary processes. Even so, echo sounding had limitations. Early systems produced single-beam measurements directly beneath a ship. To map wide areas, ships had to follow tightly spaced survey lines. Given the ocean's immense size, comprehensive coverage required enormous time investment. Later, multi-beam sonar systems were developed. These systems emit multiple sound beams at different angles, covering a broad swathe of seafloor with each pass. Multi-beam sonar dramatically increased mapping efficiency and resolution. With multi-beam technology, detailed bathymetric maps could reveal features as small as individual volcanic cones or submarine landslides. The texture of the seafloor became visible in ways previously impossible. Yet even today, not all regions have been surveyed using multi-beam sonar. Many areas are still represented by lower resolution satellite-derived data or sparse ship tracks. There are also practical challenges. Survey ships are expensive to operate. Fuel, crew, maintenance and specialised equipment require significant funding. Weather conditions can interrupt operations. Remote regions may be far from logistical support. Because of these factors, mapping efforts often focus on specific priorities: continental margins, areas of geological interest, or regions relevant to national jurisdictions. Meanwhile, vast stretches of deep ocean remain covered by widely spaced survey lines or inferred data. Another dimension of measuring depth involves submersibles and remotely operated vehicles. While sonar provides topographical data, direct observation requires physical descent. Manned submersibles like the Trieste, which reached the Challenger Deep in 1960, demonstrated that humans could reach extreme depths. More recently, specialised submersibles have returned to the Mariana Trench, gathering samples and video. However, such missions are rare and costly. Each descent requires careful engineering to withstand crushing pressure. At nearly 11,000 metres, pressure exceeds 1,000 atmospheres. Hull materials must be exceptionally strong and precisely constructed. Robotic vehicles have expanded exploration capacity. Remotely operated vehicles, ROVs, are tethered to ships and controlled from the surface. Autonomous underwater vehicles, AUVs, operate independently, following programmed routes. These vehicles can carry cameras, sonar and scientific instruments. They allow researchers to map seafloor features at close range, collect biological samples, and measure chemical properties. Still, coverage remains limited by time and resources. An AUV can survey only a certain area per mission. To map the entire ocean floor at high resolution would require thousands of such missions over many years. There is also the challenge of vertical complexity. Depth measurement often focuses on the seafloor, but the ocean is layered. Measuring depth alone does not capture temperature gradients, salinity variations, or current structures throughout the water column. Oceanographers deploy instruments called CTD sensors, measuring conductivity related to salinity, temperature, and depth to profile water properties from surface to bottom. These profiles help understand circulation patterns and heat content. Argo floats, autonomous drifting instruments, move with currents and periodically descend and ascend, transmitting data via satellite. Thousands of Argo floats operate globally, providing valuable information about upper and mid-depth waters. These systems give insight into ocean dynamics, but they do not provide full visual or biological exploration of deep habitats. When people ask how much of the ocean we have explored, depth measurement is part of the answer. We know the maximum depth, we know average depths, we know the broad shape of ocean basins, but detailed mapping, the kind that reveals fine structure everywhere, remains incomplete. It is important to avoid overstating ignorance. The deepest point in the ocean has been measured repeatedly and precisely. Major basins and ridges are well characterized. Scientists are not guessing blindly. The gap lies in granularity. Imagine having a world map that shows mountain ranges and major rivers, but lacks detailed topography for most regions. That is roughly the state of seafloor mapping today. International efforts such as the Seabed 2030 project aim to map the entire ocean floor at high resolution by the end of this decade. The goal is ambitious and reflects growing recognition of the ocean's importance to climate, ecosystems, and human activity. Accurate depth maps improve tsunami modelling. They support safe navigation. They inform conservation planning and resource management. Measuring the depths is not merely an exercise in curiosity. It is foundational to understanding how the planet functions. And yet, even as measurements accumulate, the ocean's vertical dimension continues to challenge exploration. The deeper one goes, the less frequent human visits become. Depth amplifies pressure, darkness, and isolation. The act of measuring has transformed the ocean from an unknown abyss into a mapped landscape in outline. But measuring is not the same as experiencing. Numbers define contours, but they do not reveal what moves across them. As depth profiles become clearer, attention turns naturally to what inhabits those depths. Because once the ocean floor was confirmed to exist and its contours were sketched, the next question was not only how deep it was, but what could survive there, and that realization opened an entirely new phase of exploration, focused not just on terrain, but on life in places where it once seemed impossible. For much of history, the ocean was approached in fragments. Sailors understood winds and currents that mattered to trade. Coastal communities understood tides and fisheries. Natural philosophers speculated about salinity and marine life. But there was no unified science of the ocean, no single discipline devoted to understanding it as an interconnected system. That began to change in the 19th century. Before that point, knowledge of the sea was scattered across navigation manuals, travel accounts, and isolated scientific observations. A captain might record unusual currents. A biologist might describe a newly collected shell. A geologist might speculate about seabed composition. But these insights were not yet part of a coordinated effort to study the ocean as a whole. The shift toward organised ocean study required both intellectual curiosity and practical motivation. One of the strongest practical motivations was communication. As global trade expanded, the idea of laying telegraph cables across the ocean floor became increasingly important. The first successful transatlantic telegraph cable was completed in 1866, but its planning required understanding depth, seabed composition, and ocean conditions. Suddenly, the deep ocean was not merely a distant curiosity, it was a route for infrastructure. Engineers needed reliable information about terrain thousands of meters below the surface. At the same time, scientific thinking was evolving. The 19th century saw the rise of systematic data collection in fields like geology, biology, and meteorology. There was growing interest in classifying and understanding natural systems on a global scale. Within this context, the ocean began to attract attention as an integrated subject of study. One of the most significant milestones in this transformation was the voyage of the HMS Challenger from 1872 to 1876. Commissioned by the British government, the expedition was designed specifically for scientific research rather than trade or military purposes. The Challenger carried a team of scientists tasked with studying the physical, chemical, geological, and biological properties of the oceans. Over nearly 4 years, the ship travelled approximately 68,000 nautical miles, taking depth measurements, collecting sediment samples, dredging marine organisms, and recording water temperatures at various depths. This was not exploration in the dramatic sense of discovering new continents. It was methodical and data-driven. Stations were established at regular intervals. Instruments were deployed carefully. Observations were documented in detail. The results were transformative. The expedition confirmed the existence of deep ocean basins and trenches. It collected thousands of previously unknown marine species. It demonstrated that life existed even in the deepest waters sampled. It gathered temperature profiles showing how water properties changed with depth. When the expedition concluded, it produced a series of comprehensive scientific reports spanning dozens of volumes. These publications laid the foundation for oceanography as a distinct scientific field. Oceanography, in its emerging form, combined elements of multiple disciplines. It drew from physics to understand currents and waves. It used chemistry to analyze salinity and dissolved gases. It relied on biology to classify marine life. It incorporated geology to study sediments and seabed structure. The ocean was no longer just a setting for other sciences. It became the subject itself. In the decades following the Challenger expedition, oceanographic research expanded. Institutions dedicated to marine science were established. In the United States, the Woods Hole Oceanographic Institution was founded in 1930. Similar centres developed in Europe and elsewhere. These institutions provided stable platforms for long-term research, training scientists, developing instruments, and organising expeditions. Technological advances accelerated progress. Thermometers designed to withstand high pressure allowed accurate temperature measurements at depth. Nansen bottles, developed in the late 19th century, enabled collection of water samples from specific depths. These bottles would be lowered into the ocean, triggered to close at predetermined depths, and then retrieved for analysis. With these tools, oceanographers began to map temperature and salinity patterns across large regions. They identified water masses with distinct properties and traced their movement through ocean basins. Understanding circulation patterns became a central focus. Scientists discovered that ocean currents were driven not only by wind at the surface, but also by differences in water density caused by temperature and salinity variations. This deep circulation system, sometimes called thermohaline circulation, connects the world's oceans in a slow, global conveyor belt. These findings had implications far beyond marine science. Ocean circulation influences climate, distributing heat around the planet. Without these currents, regional climates would differ dramatically. As oceanography matured, it divided into subfields. Physical oceanography focused on currents, waves, and circulation. Chemical oceanography examined dissolved substances and chemical processes. Biological oceanography studied marine organisms and ecosystems. Geological oceanography investigated seafloor structure and sedimentation. This specialization allowed deeper investigation into each component, while maintaining awareness of their interconnections. The mid-20th century brought further expansion, partly driven by global conflict. During World War II, understanding ocean conditions became strategically important. Submarine warfare, amphibious landings, and sonar detection required detailed knowledge of water properties and seafloor topography. After the war, many of the technologies developed for military purposes were adapted for scientific research. Sonar systems improved seafloor mapping. New vessels were built specifically for oceanographic missions. One of the most dramatic discoveries of the 20th century was the system of mid-ocean ridges encircling the globe. Combined with evidence from magnetic anomalies in seafloor rocks, these ridges provided support for the theory of plate tectonics. The ocean floor was revealed as dynamic, continuously created at ridges and consumed at subduction zones. This insight reshaped geology as a whole. Oceanography had contributed to understanding the structure and evolution of Earth itself. Another major breakthrough came with the discovery of hydrothermal vents in 1977. Using deep-diving submersibles, scientists observed ecosystems thriving around these vents, supported not by sunlight, but by chemical energy from Earth's interior. This discovery challenged assumptions about the limits of life. It expanded the definition of habitable environments and influenced astrobiology, the study of life beyond Earth. Oceanography, which began as a systematic attempt to measure depths and collect samples, had become a window into fundamental planetary processes. Despite these advances, the ocean remained vast and only partially explored. The birth of oceanography did not eliminate unknowns. It provided tools and frameworks for investigating them. The field also became increasingly international. Oceans do not respect national boundaries, and understanding global circulation or climate interactions requires cooperation across countries. Programs like the International Indian Ocean Expedition in the 1960s and later global initiatives coordinated research efforts across continents. Satellite technology added another dimension. From orbit, scientists could measure sea surface temperature, chlorophyll concentrations, and sea level changes. These observations complemented ship-based measurements, providing continuous global coverage of surface conditions. Yet satellites could not replace in situ measurements at depth. Oceanography became a balance between remote sensing and direct sampling. Over time, long-term monitoring programs were established. Time series stations collected data over decades, tracking changes in temperature, acidity, and biological activity. These records became crucial for understanding climate change and ocean health. As atmospheric carbon dioxide levels rose due to human activity, the ocean absorbed a significant portion of that carbon. Chemical oceanographers studied how this absorption affected pH levels, leading to ocean acidification. This process has implications for marine organisms, particularly those that build shells or skeletons from calcium carbonate. Thus, oceanography evolved from exploratory science into a critical component of environmental monitoring and policy. Even with institutional support and technological sophistication, the field faces challenges. The ocean's size means that even well-funded programs cannot cover everything. Deep-sea exploration remains expensive. Harsh conditions limit access. Funding priorities also influence research focus. Coastal regions where human activity is concentrated often receive more attention than remote deep basins. Fisheries management, pollution studies, and climate research drive much of modern oceanographic work. Nevertheless, the foundational shift that occurred in the 19th century remains significant. Before the birth of oceanography, the sea was studied in fragments. Afterward, it became recognized as a coherent system worthy of dedicated investigation. This transformation altered how humanity relates to the ocean. It is no longer just a route for ships or a source of food. It is a dynamic system that regulates climate, supports biodiversity, and interacts with geological processes. And yet, even as oceanography matured, it did not eliminate the sense of frontier. Each new instrument revealed additional complexity. Each expedition uncovered species or structures previously unknown. The birth of oceanography marked the beginning of systematic exploration, not its completion. As we move further into the 21st century, oceanography continues to expand its tools and questions. Autonomous vehicles explore depths beyond regular human reach. Genetic analysis reveals microbial communities invisible to the naked eye. Long-term datasets track subtle shifts over decades. The ocean, once a blank blue space on maps, has become layered with data points, contour lines, and chemical profiles. But data does not erase scale. The ocean remains immense. From here, attention naturally shifts to one of the most challenging environments oceanography confronts: the deep sea, where sunlight never penetrates and pressure increases beyond intuitive comprehension. Because understanding the birth of the discipline explains how we began studying the ocean, but it does not yet fully capture what it means to enter regions where light disappears entirely and familiar reference points vanish. If you stand on a beach at midday and look out across the water, it is difficult to imagine darkness as the ocean's dominant condition. Sunlight reflects off the surface. Waves shimmer. The water near shore may appear turquoise or deep blue, depending on depth and sediment. It feels open and visible, but that brightness is a thin layer. Sunlight penetrates water only so far. In the clearest tropical seas, light may reach depths of about 200 meters. Beyond that, it fades rapidly. By around 1,000 meters, there is no sunlight at all. Below that depth lies a region that remains in permanent darkness, regardless of time of day or weather at the surface. This means that the majority of the ocean exists without light. To understand how much, consider that the average ocean depth is roughly 3,700 meters. The sunlit zone, where photosynthesis can occur, represents only a small fraction of the total volume. Beneath it stretches a vast, dark environment that covers most of the planet. This region is often divided into layers. The uppermost is the epipelagic zone, extending from the surface to about 200 meters. This is where most visible marine life familiar to us resides. Fish, plankton, coral reefs. It is the layer where light supports photosynthesis. Below that lies the mesopelagic zone, sometimes called the twilight zone, ranging roughly from 200 to 1,000 meters. Here, light is dim and blue. Photosynthesis is no longer possible, but faint traces of sunlight remain. Creatures in this zone often have large eyes adapted to detect minimal light. Below the twilight zone begins the bathypelagic zone, where darkness is complete. This extends down to about 4,000 meters. Deeper still are the abyssopelagic and hadal zones, reaching into trenches that descend beyond 10,000 meters. When we speak of exploring the ocean, it is largely this dark majority that remains least visited. For centuries, scientists assumed that life could not exist in these depths. The pressure alone seemed prohibitive. At 1,000 meters, pressure is roughly 100 times greater than at sea level. At 4,000 meters, it is about 400 times greater. In the deepest trenches, it exceeds 1,000 atmospheres. In addition to pressure, temperatures drop near freezing. Sunlight is absent. Food appears scarce. From a surface perspective, it seemed unlikely that complex ecosystems could thrive under such conditions. That assumption was challenged in the 19th century when deep-sea dredging began to recover organisms from previously unexplored depths. The HMS Challenger expedition brought up samples from thousands of meters below the surface, revealing starfish, crustaceans, and other organisms adapted to darkness. Later, the development of deep-diving submersibles allowed direct observation. In 1960, the bathyscaphe Trieste descended to the Challenger Deep in the Mariana Trench. Observers reported seeing life even at nearly 11,000 meters, though subsequent analysis refined interpretations of what was visible. With improved technology in the late 20th century, scientists began documenting deep-sea life more extensively. Remotely operated vehicles equipped with cameras revealed environments unlike anything on land. In total darkness, many organisms produce their own light through bioluminescence. Chemical reactions within specialized cells generate light that can attract prey, deter predators, or communicate with potential mates. In the twilight zone, lanternfish use light-producing organs to blend with faint light from above, disguising their silhouettes from predators below. In deeper regions, anglerfish use glowing lures to attract prey in darkness. The absence of sunlight reshapes the rules of survival. In surface waters, food chains begin with phytoplankton converting sunlight into energy. In the deep sea, energy sources differ. Much of the deep ocean relies on marine snow, a slow drift of organic particles descending from upper layers. Dead plankton, fecal pellets, and other debris fall gradually, providing nutrients to organisms below. In some regions, however, energy comes from Earth's interior. Hydrothermal vents release mineral-rich fluids heated by magma beneath the sea floor. Around these vents, bacteria use chemical reactions to produce energy, supporting entire ecosystems independent of sunlight. The discovery of hydrothermal vent communities in 1977 revealed giant tube worms, clams, and shrimp clustered around vent openings. These organisms live in partnership with bacteria capable of chemosynthesis. This finding altered scientific understanding of life's limits. It suggested that ecosystems could exist in complete darkness, relying on chemical energy rather than solar radiation. Yet hydrothermal vents occupy only limited areas. The majority of the deep sea consists of vast plains known as abyssal plains. These regions are relatively flat and covered in fine sediment. They stretch across thousands of kilometres. Exploring abyssal plains presents logistical challenges. There are few obvious landmarks. Depths are extreme. Deploying and retrieving equipment requires time and favourable weather conditions. Even with modern, remotely operated vehicles, covering large areas at close range is slow. A submersible moving a few metres above the seafloor captures high-resolution imagery, but its field of view is narrow compared to the vastness around it. As a result, large portions of the deep ocean floor have never been directly observed by camera. The darkness also complicates perception. Human vision depends on light. In deep-sea exploration, artificial lighting must be used. Bright lights illuminate only a small area, while beyond their reach lies blackness. This creates a limited window into an immense environment. Cameras record what is directly ahead, but not what extends beyond the beam. There is also the issue of scale. The deep ocean covers more than half of Earth's surface. Even if every deep-sea expedition mapped several square kilometres in detail, it would take an extraordinary number of missions to achieve comprehensive coverage. The deep ocean is sometimes described as the largest habitat on the planet. It hosts a diversity of life forms, many of which remain undescribed. Estimates suggest that a significant percentage of deep-sea species have yet to be formally identified. Microbial life adds further complexity. Bacteria and archaea inhabit sediments and water columns, at depths where multicellular life is sparse. These microorganisms play roles in nutrient cycling and chemical processes that influence global systems. Despite this biological richness, the deep ocean remains remote from everyday experience. Most people will never see it directly. Its darkness keeps it out of sight, and, often, out of mind. Technological innovation continues to expand access. Autonomous underwater vehicles can operate without tethers, mapping terrain and collecting data for extended periods. Deep-sea observatories installed on the seafloor transmit data in real time, monitoring conditions continuously. Still, these efforts sample rather than saturate. They provide insight into selected sites rather than universal coverage. The absence of light also affects how information is gathered. Sonar becomes essential as sound travels efficiently through water. Acoustic methods detect objects, measure depth, and even identify schools of fish. But acoustic data differs from visual data. It provides shape and movement patterns without colour or fine detail. When we ask how much of the ocean has been explored, the dark zones account for much of the uncertainty. Surface waters are monitored extensively by satellites and ships. Coastal ecosystems are studied regularly. The deep ocean, particularly beyond continental margins, receives less direct attention. This does not mean it is entirely unknown. Scientists understand pressure gradients, temperature profiles, and major topographical features, but detailed biological surveys and continuous observation remain limited. The phrase, "a world without light," is literal in this context. It is an environment shaped by darkness, high pressure, and cold temperatures. It operates under different constraints than surface ecosystems. Exploration in such an environment requires specialized engineering. Submersibles must withstand crushing forces. Instruments must function reliably in cold, corrosive salt water. Communication with surface vessels may rely on acoustic signals rather than direct cables. Each mission into deep darkness represents careful planning and significant investment. Yet even with these efforts, vast stretches of the bathypelagic and abyssal zones have never been seen by human eyes or cameras. Understanding this helps clarify what it means to say we have explored only a small percentage of the ocean. It is not that the ocean is entirely mysterious, it is that its largest region, defined by darkness, remains only partially observed. As exploration continues, attention increasingly turns to how life adapts to these conditions and what processes occur unseen in darkness. Because once the presence of life in deep zones was established, The next challenge was understanding how it survives under extreme pressure and limited energy, and that leads naturally into examining the physical constraints of the abyss and the engineering required to reach it. For a long time, it seemed reasonable to assume that life had limits. Sunlight fuels plants, plants feed animals, remove sunlight, increase pressure to crushing levels, drop temperatures close to freezing, and the system should fail. That was the expectation well into the 20th century. The deep ocean, especially far below the reach of light, was thought to be sparse at best and empty at worst. That assumption began to weaken in the late 19th century, when dredging equipment pulled living organisms from depths previously assumed uninhabitable. Starfish, crustaceans and worms appeared in nets raised from thousands of meters below. Still, many scientists believed that the deepest regions would prove barren. Then came a discovery that forced a fundamental reconsideration. In 1977, a team of scientists exploring the Galapagos Rift in the Pacific Ocean used a deep-diving submersible called Alvin to investigate unusual temperature readings on the seafloor. What they found were hydrothermal vents, cracks in the Earth's crust releasing superheated, mineral-rich water into the surrounding ocean. Around these vents clustered dense communities of life. Giant tube worms, some over 2 meters long, stood upright in white and red clusters. Clams and mussels formed thick beds. Shrimp and crabs moved across the dark landscape. The water around them was chemically extreme, rich in hydrogen sulfide and other compounds toxic to most surface life. The most striking aspect was not just the abundance of organisms, but the source of their energy. These ecosystems did not depend on sunlight. They relied on chemosynthesis. Specialized bacteria living inside the tissues of tube worms and other organisms converted chemical compounds from vent fluids into energy. Instead of photosynthesis powered by light, this was chemistry-powered metabolism. The discovery demonstrated that life could exist entirely independent of solar energy. It redefined what habitable could mean. Since that initial finding, hydrothermal vents have been identified in multiple ocean basins. They occur along mid-ocean ridges where tectonic plates diverge and magma rises closer to the sea floor. Cold seawater seeps into cracks, becomes heated by underlying magma, dissolves minerals, and then rises back into the ocean through vent openings. These vents are not permanent. They can become inactive as geological conditions change. Yet while active, they support thriving ecosystems. The organisms living there are highly specialized. Tube worms lack mouths and digestive systems. Instead, they house symbiotic bacteria within their tissues. The bacteria perform chemosynthesis, providing nutrients to their hosts. In return, the worms supply the bacteria with access to vent chemicals and oxygen from surrounding seawater. Clams and mussels near vents also host symbiotic bacteria. Some shrimp species have reduced eyesight and rely on chemical sensing rather than vision. The entire community operates in darkness under high pressure. Hydrothermal vents are not the only example of unexpected deep-sea life. Cold seeps, areas where hydrocarbons like methane seep from the seafloor, also host chemosynthetic communities. Similar to vents, bacteria convert chemical energy into organic matter, supporting specialized organisms. Beyond these chemically active sites, life persists across the broader abyssal plains. These regions receive limited organic input from surface waters in the form of marine snow, tiny particles drifting downward. Despite the scarcity, organisms survive. Sea cucumbers, brittle stars, and deep-sea fish move slowly across sediment. Many species grow slowly and reproduce infrequently. Energy conservation becomes a survival strategy. Adaptations to high pressure are particularly remarkable. At extreme depths, cellular structures must remain functional despite intense compression. Proteins and membranes in deep-sea organisms have molecular features that maintain stability under pressure. Enzymes function differently than those in surface-dwelling relatives. Temperature also plays a role. Deep ocean temperatures hover near 2 to 4 degrees Celsius in many regions. Metabolic rates are often slower. Lifespans can be extended. Some deep-sea species exhibit delayed maturation and long reproductive cycles. Bioluminescence is widespread. In the absence of sunlight, light production becomes a versatile tool. Some organisms use it to lure prey. Others use it to confuse predators or communicate. Anglerfish carry bioluminescent lures extending from their heads. When smaller fish approach the glowing appendage, they're captured by large jaws. Certain squid eject glowing ink as a defensive distraction. In the mesopelagic twilight zone, bioluminescence may serve camouflage. By producing light on their undersides that matches faint light from above, fish reduce their silhouettes when viewed from below. The prevalence of bioluminescence suggests it is one of the dominant forms of communication and interaction in dark waters. Microbial life extends even further into extreme conditions. Bacteria have been found living within deep-sea sediments, kilometers below the ocean floor. Some survive on minimal energy, metabolizing slowly over long timescales. In the deepest trenches, such as the Mariana Trench, organisms endure pressures exceeding 1,000 atmospheres. Amphipods, shrimp-like crustaceans, have been observed at these depths. Specialized fish species known as snailfish have been recorded near trench floors. These fish possess soft bodies and reduced skeletal structures that tolerate pressure without rigid elements prone to collapse. Their cellular chemistry is adapted to function under compression. The presence of life in trenches challenges earlier assumptions that extreme pressure would prevent complex organisms from surviving. Even more surprising is the persistence of microbial life in environments once considered sterile. Studies of sub-seafloor sediments reveal microbial communities active at depths of hundreds of meters below the seabed. These organisms may subsist on limited chemical gradients and trace nutrients. Such findings extend the boundaries of what is considered viable habitat. The idea that life shouldn't exist in these environments arises from surface-based intuition. On land, extreme pressure and absence of light typically correspond with inhospitable conditions. But evolution operates through adaptation. Given time and genetic variation, organisms occupy available niches. In the deep ocean, the absence of sunlight does not eliminate energy entirely. Chemical reactions, detrital input, and geological processes provide alternative pathways. Exploration continues to uncover new species. Many deep-sea organisms remain undescribed. Sampling is challenging, and some species may be damaged when brought to the surface due to pressure changes. Advanced imaging and genetic techniques help identify organisms without necessarily retrieving them physically. Environmental DNA sampling allows scientists to detect species presence by analyzing genetic material in water samples. Still, direct observation remains essential for understanding behavior and ecological interactions. When people hear that most of the ocean is unexplored, part of that refers to biological diversity. Estimates suggest that a large proportion of marine species, particularly in deep environments, have not yet been formally described by science. This does not mean that these organisms are invisible or impossible to detect. It means that systematic cataloguing has not yet been completed. The scale of the ocean makes comprehensive biological surveys difficult. A forest can be surveyed by teams walking through it. A deep-sea plain requires submersibles, remote vehicles, and precise navigation. The existence of life in extreme deep-sea environments has broader implications. It informs astrobiology, the study of potential life beyond Earth. If organisms can survive without sunlight in chemically active environments on our planet, similar conditions on icy moons such as Europa or Enceladus may also be candidates for life. Thus, exploring life in places once considered impossible expands not only marine biology, but planetary science. At the same time, these discoveries highlight how limited our direct exploration remains. Each new vent field discovered suggests others yet to be found. Each trench survey reveals species previously unknown. Life where it shouldn't exist has become life that challenges assumptions. It reveals that absence of light does not equal absence of biology. Pressure does not eliminate adaptation. The deep ocean is not empty darkness. It is structured by physical constraints and filled with organisms uniquely suited to them. Understanding these ecosystems requires continued descent into environments that remain technically demanding and financially costly to reach, because once the existence of life was confirmed in darkness and pressure, the question shifted from whether life could exist there to how much of it remains unseen. And as research continues, the limits of exploration are defined not by absence of curiosity, but by the difficulty of sustained access to a habitat that covers most of the planet and operates beyond the reach of sunlight. If darkness defines much of the deep ocean, pressure defines how difficult it is to reach. On land, pressure is something you rarely think about. At sea level, the air around you exerts about 1 atmosphere of pressure. It is constant, invisible, and harmless because your body is adapted to it. Even climbing a mountain only changes that pressure gradually. Underwater, the situation changes quickly. Water is far denser than air. For every 10 meters you descend beneath the ocean's surface, pressure increases by roughly 1 atmosphere. At 100 meters, pressure is about 10 times what you experience at sea level. At 1,000 meters, it is about 100 times greater. In the deepest trenches near 11,000 meters, pressure exceeds 1,000 atmospheres. To put that into perspective, imagine the weight of a small car pressing down on an area the size of a postage stamp. That is the kind of force exerted at extreme depths. For human beings, such pressure is instantly lethal without protection. Even at relatively shallow depths, divers must carefully manage pressure changes to avoid injury. At great depths, specialized equipment becomes not just helpful, but essential. This is one of the main reasons why so much of the ocean remains unexplored in direct terms. It is not simply dark and cold. It is physically hostile to unprotected structures. Early attempts to descend beneath the surface were limited to shallow waters. Diving bells, used as early as ancient Greece, allowed brief underwater stays by trapping air inside a chamber lowered into the water. These devices were effective only at modest depths. As technology advanced, surface-supplied diving suits allowed divers to reach greater depths. Heavy suits with reinforced helmets provided protection against water pressure, but mobility was limited, and depth limits remained relatively shallow compared to the vast ocean. The real challenge begins beyond the continental shelf, where depths exceed several hundred meters and then drop into the thousands. To reach such depths, entirely different engineering approaches are required. The bathyscaphe Trieste, which descended to the Challenger Deep in 1960, was a remarkable example. It consisted of a pressurized sphere suspended beneath a large float filled with gasoline. Gasoline was used because it is less dense than water and provides buoyancy without compressing significantly under pressure. The crew cabin was a thick steel sphere designed to withstand immense external pressure. Even so, the descent was slow and carefully controlled. The mission demonstrated that reaching the deepest parts of the ocean was possible, but it was not routine. Only a handful of crewed descents have reached similar depths since then. Modern deep-sea submersibles are built using advanced materials such as titanium or specially designed composites. The hull must be precisely engineered. Any flaw can lead to catastrophic failure. Pressure acts uniformly from all directions. It does not push from one side, it compresses from every angle. This means that structural integrity must be maintained across the entire surface of a vessel. At extreme depths, even small imperfections can become critical weaknesses. Beyond crewed submersibles, remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, have expanded exploration capacity. These robotic systems can reach depths that are risky or impractical for human occupants. Even so, pressure remains a limiting factor. Electronic components must be sealed within pressure-resistant housings. Cameras require thick viewports made from materials that resist cracking. Moving parts must function reliably in cold, high-pressure salt water. Maintenance and repair become complicated when equipment operates kilometers below the surface. Pressure also affects the organisms being studied. When deep-sea creatures are brought to the surface, the dramatic change in pressure can damage their bodies. Some species cannot survive decompression. Their tissues are adapted to constant compression, and rapid pressure loss can cause structural failure. This makes in situ observation important. Studying organisms in their natural high-pressure environment provides more accurate information about behaviour and physiology. The abyssal plain, which lies between roughly 4,000 and 6,000 metres, covers vast areas of the ocean floor. At these depths, pressure ranges from 400 to 600 atmospheres. Human visits are rare. Robotic missions are more common, but still limited in coverage. In the Hadal zone, found in deep ocean trenches beyond 6,000 metres, pressure becomes even more extreme. These regions are narrow and geographically isolated compared to the broader abyssal plains. Exploring them requires specialised equipment rated for ultra-deep conditions. Because of these engineering challenges, deep-sea exploration is expensive. Designing and building vehicles capable of withstanding such pressure involves significant research and testing. Launching missions require support ships, trained crews, and favourable weather conditions. All of this contributes to why only a small fraction of the deep ocean has been directly observed. It is not lack of interest that limits exploration. It is the combination of cost, risk, and scale. Pressure shapes not only exploration logistics but also ecological dynamics. Organisms living at depth must have cellular structures capable of functioning under compression. Proteins and membranes behave differently under high pressure. Enzymatic reactions can be altered. Evolution has produced adaptations that maintain biochemical stability. For example, certain deep-sea fish accumulate molecules that stabilize proteins against pressure-induced distortion. Membrane composition may differ to preserve fluidity at both low temperatures and high pressures. Reproductive strategies may also adapt to these conditions. Many deep-sea species produce fewer offspring and invest more energy in each one, reflecting limited food availability and slow growth rates. The physical constraints of the abyss influence biological patterns. Pressure also affects sound propagation. Sound travels efficiently through water, and deep layers can channel acoustic signals over long distances. This has implications for communication among marine mammals and for human activities such as sonar mapping. In addition, pressure influences sediment structure. On abyssal plains, fine particles settle slowly from above, forming thick layers of soft sediment. These sediments may record millions of years of geological and biological history. Sampling such sediments requires coring equipment capable of penetrating compacted layers under high pressure. When considering how much of the ocean has been explored, pressure serves as a practical boundary. Surface waters and shallow shelves are relatively accessible. Deeper regions demand more complex technology and greater financial investment. Even today, the majority of ultra-deep trenches have been visited only a handful of times, if at all. The ocean's vertical dimension is what distinguishes it from most terrestrial environments. While mountain peaks present challenges due to low pressure and thin air, deep-sea environments present the opposite extreme. The direction of pressure change is reversed. On land, increasing altitude reduces pressure gradually. Underwater, descending increases pressure rapidly and continuously. This simple physical fact explains much about exploration patterns. Satellites can image Earth's surface from orbit. Land vehicles can traverse continents. Aircraft can survey large areas efficiently. The deep ocean cannot be accessed remotely in the same way without specialized descent. Even communication is more difficult. Radio waves do not travel well through seawater. Communication with deep-sea vehicles often relies on acoustic signals, which have lower bandwidth and slower data transmission rates. These constraints slow the pace of exploration. At the same time, technology continues to improve. New materials, better battery systems, and improved navigation algorithms expand the range and duration of deep-sea missions. International collaborations share costs and data. Mapping initiatives aim to accelerate coverage. But even with advances, pressure remains constant. It has not become less intense with improved engineering. It simply becomes more manageable. When people compare ocean exploration to space exploration, they sometimes assume that space is inherently more hostile. In some respects, it is. But the deep ocean presents a different kind of hostility, one defined by crushing force rather than vacuum. Both environments require specialized technology. Both limit direct human presence. In the case of the ocean, the barrier is not distance from Earth, but the properties of water itself. Understanding the pressure of the abyss clarifies why so much of the ocean remains less directly explored than surface environments. It is not simply hidden, it is difficult to access safely and repeatedly. And because each descent requires careful planning and substantial resources, coverage accumulates slowly. As exploration technology advances, pressure becomes less of an absolute barrier and more of an engineering problem, but it remains a defining characteristic of the deep sea. From here, attention naturally turns to the tools designed to operate under such conditions, because overcoming pressure is only one part of the challenge. Navigating, mapping, and observing within this environment requires machines capable of descending, operating, and returning reliably. And those machines, increasingly robotic rather than crewed, have become the primary means by which we continue extending our reach into the abyss. Human beings are not built for the deep ocean. Our bodies are adapted to air, moderate pressure, and light. Even with advanced diving equipment, we can only descend a few hundred meters safely. Beyond that, pressure and darkness demand something else entirely. So if we cannot go there easily ourselves, we send machines. The story of ocean exploration in the last century is largely the story of technology learning to dive in our place. Early submersibles were experimental and rare. The bathyscaphe Trieste demonstrated that humans could reach the deepest known point in the ocean, but such missions were exceptional rather than routine. Crewed descents remain technically demanding and expensive. Each mission requires meticulous preparation, specialized materials, and careful safety protocols. Because of these constraints, much of modern deep-sea exploration relies on remotely operated vehicles, or ROVs. An ROV is connected to a surface ship by a thick cable known as an umbilical. This tether provides power, transmits data, and allows operators to control the vehicle in real time. From a control room aboard the ship, pilots use joysticks and monitors to maneuver the vehicle, adjust cameras, and operate robotic arms. The cable may extend thousands of meters into the ocean, linking the surface crew to the vehicle moving across the seabed. High-intensity lights illuminate the dark surroundings, cameras transmit live video. Manipulator arms collect samples of sediment, rocks, or biological specimens. Because ROVs are tethered, they can remain underwater for extended periods without worrying about battery life in the same way autonomous vehicles do. The surface ship supplies power continuously. This setup has advantages. Scientists can make immediate decisions based on what they see. If something unexpected appears in the camera frame, they can investigate right away. They can adjust sampling strategies dynamically. But the tether also imposes limitations. The cable can become tangled on rough terrain. Strong currents constrain it. The operational area is constrained by the ship's position and the cable's length. To complement ROVs, autonomous underwater vehicles, or AUVs, have become increasingly important. Unlike ROVs, AUVs are not tethered. They are programmed before deployment with a mission plan and then released into the water. They navigate independently using onboard sensors and return to the surface after completing their tasks. AUVs can map large areas efficiently. Equipped with multi-beam sonar systems, they travel close to the seafloor. producing high-resolution bathymetric maps. Flying lower than a ship-based sonar system allows them to capture finer detail. Because they operate without tethers, AUVs can access complex terrain more easily. They can follow pre-programmed grid patterns to ensure systematic coverage. However, autonomy brings its own challenges. Communication with an AUV while submerged is limited. Acoustic signals can transmit basic instructions, but high-bandwidth data transfer is not possible in real time. Most detailed data are retrieved only after the vehicle surfaces. Battery life constrains mission duration. Energy must power propulsion, sensors, navigation systems, and onboard computers. Advances in battery technology have extended mission lengths, but trade-offs remain. Together, ROVs and AUVs form the backbone of deep-sea exploration. There are also hybrid systems that combine aspects of both. Some vehicles operate autonomously during mapping phases, and then switch to tethered mode for detailed investigation. Beyond mobile vehicles, fixed instruments contribute to ocean exploration. Seafloor observatories, installed in certain regions, provide continuous monitoring of environmental conditions. These observatories may include sensors for temperature, pressure, seismic activity, and chemical composition. Some are connected to shore by undersea cables, allowing real-time data transmission. Others store data locally until maintenance visits retrieve them. Long-term monitoring is valuable because many ocean processes unfold slowly. Currents shift over seasons. Chemical concentrations change over years. Without continuous observation, patterns can be missed. Surface technology also plays a role. Research vessels are specialized ships designed to support oceanographic missions. They carry laboratories, winches, cranes, and dynamic positioning systems that allow them to maintain precise location even in rough seas. Dynamic positioning uses thrusters and GPS to keep a ship stable above a specific point. This stability is essential when deploying deep-sea equipment. Even slight drift can affect tether alignment or mapping accuracy. Satellite systems contribute by monitoring surface conditions. They measure sea surface temperature, wave height, and ocean color, which indicates phytoplankton concentration. While satellites cannot see into the deep ocean directly, they provide context for what lies below. Another important technological development is deep-sea drilling. Scientific drilling programs use specialized vessels to bore into the ocean floor, retrieving sediment cores that record millions of years of Earth's history. These cores provide information about past climates, volcanic activity, and biological evolution. The drilling process must account for pressure and sediment stability. Equipment operates under challenging conditions far from shore. In recent years, advancements in miniaturization and robotics have expanded capabilities further. Smaller, more affordable AUVs allow broader participation in exploration. Universities and smaller research institutions can deploy compact vehicles for targeted missions. Underwater gliders represent another class of autonomous systems. These vehicles move through the water by adjusting buoyancy and gliding forward in a sawtooth pattern. They consume minimal energy and can operate for months, collecting data on temperature, salinity, and other properties. Gliders do not dive to extreme depths like some AUVs, but they contribute valuable data on upper and midwater layers across large distances. Navigation underwater presents unique challenges. GPS signals do not penetrate water effectively. Instead, underwater vehicles rely on inertial navigation systems, acoustic beacons, and Doppler velocity logs to estimate position. Precision is critical when mapping. Small navigation errors can distort bathymetric data. Combining multiple sensors improves accuracy. Lighting technology is also improved. Deep-sea cameras require powerful illumination. Modern LED systems provide bright, energy-efficient lighting that reveals fine detail without excessive heat generation. High-definition and even ultra-high-definition cameras capture detailed imagery, allowing scientists to observe subtle features in organisms and terrain. Despite these advancements, exploration remains selective rather than comprehensive. Each mission focuses on specific research questions or target areas. The ocean's total area is so vast that even thousands of missions cover only a fraction in close detail. Cost remains a significant factor. Operating a large research vessel can cost tens of thousands of dollars per day. Designing and maintaining deep-sea vehicles requires specialized expertise. Funding agencies must balance ocean research with other scientific priorities. As a result, exploration tends to concentrate on regions of particular interest, such as hydrothermal vents, coral reefs, or areas relevant to climate studies. Private initiatives have also entered the field. Some expeditions are funded by philanthropists or commercial entities. Advances in technology have lowered certain barriers, but deep-sea missions remain complex undertakings. Data management presents another challenge. High-resolution mapping generates enormous datasets. Storing, processing, and analysing this information requires substantial computational resources. Sharing data globally allows collaboration and reduces duplication of effort. International projects aim to coordinate mapping efforts to accelerate coverage. One example is the Seabed 2030 initiative, which seeks to produce a complete high-resolution map of the global ocean floor by the end of this decade. Achieving that goal depends heavily on integrating data from multiple sources and technologies. Even with all these tools, some aspects of the ocean remain elusive. Ultra-deep trenches are visited infrequently. Remote regions far from major research hubs receive less attention. Technology allows us to dive deeper and see more than ever before. But it does not eliminate the ocean's scale or the time required to explore it thoroughly. The phrase, "the technology that dives for us," reflects a shift in exploration philosophy. Rather than sending humans into every environment directly, we extend our reach through machines. These machines withstand pressure, operate in darkness, and collect data we could not gather otherwise. In many cases, they act as our eyes and hands in places we cannot easily inhabit. As exploration continues, artificial intelligence is being integrated into autonomous systems. Machine learning algorithms help vehicles identify features of interest automatically, adjust mission parameters, and process large data sets more efficiently. This trend suggests that future exploration may become increasingly automated, with fleets of autonomous vehicles mapping and monitoring continuously. Yet even as machines expand coverage, interpretation remains a human task. Scientists analyze data, design missions, and decide which questions to pursue. Technology provides access, curiosity directs it. When considering how much of the ocean has been explored, it is clear that progress depends heavily on the capabilities of these machines. Without them, deep-sea exploration would be extremely limited. Even so, the percentage of the ocean mapped in fine detail remains relatively small compared to the total area. The machines dive for us, but they do so methodically, one mission at a time. From here, it becomes important to look not just at the vehicles themselves, but at the actual coverage achieved. Because despite the sophistication of our tools, there are still vast regions of the ocean floor that remain mapped only in broad outline. And understanding those gaps clarifies what we mean when we talk about unexplored ocean territory. If you were to look at a modern digital map of the ocean floor, it might appear complete. Coloured gradients show depth changes, long ridges snake through basins, trenches carve narrow lines along tectonic boundaries. At first glance, it looks as though the entire seabed has been charted with clarity. But appearances can be misleading. Much of the global ocean floor map that you see today is based on indirect measurements. Satellite altimetry, which measures tiny variations in sea surface height caused by gravitational differences from underwater features, provides broad outlines. From those outlines, scientists can infer the presence of mountains, ridges, and trenches. This method is powerful, but it's not high resolution. Imagine flying in an airplane high above a landscape and trying to sketch the terrain based only on slight bulges in cloud cover. You might correctly identify large mountain ranges or deep valleys, but you would miss smaller hills, cliffs, and detailed textures. That is similar to how much of the ocean floor is currently represented. High-resolution mapping requires ships equipped with multi-beam sonar, travelling systematically across an area, often in tight parallel lines. The sonar sends out sound waves in a fan-shaped pattern beneath the ship, measuring the time it takes for echoes to return from the seabed. From these data, detailed bathymetric maps are constructed. This process works well, but it's slow relative to the ocean's size. The global ocean covers about 361 million square kilometres. Even with modern survey vessels, mapping every square kilometre in fine detail would take significant time and resources. As of recent estimates, only a modest percentage of the seafloor has been mapped using high-resolution multi-beam sonar. The exact percentage changes as new data are added, but it remains far from complete. What does that mean in practical terms? It means that there are underwater mountains, ridges, valleys, and plains that have never been imaged in high detail. Their approximate shapes are known from satellite-derived data, but their textures, slopes, and small-scale features remain uncertain. It also means that potential habitats for marine life exist in areas that have never been closely observed. The ocean floor is not uniform. It contains a wide range of environments. There are mid-ocean ridges where tectonic plates diverge. There are subduction zones where plates converge, forming deep trenches. There are seamounts, underwater mountains that rise thousands of meters from the seabed. There are submarine canyons cutting through continental slopes. Each of these features influences currents, sediment deposition, and biological communities. Yet many seamounts have never been visited by submersible or even mapped in high detail. Some have been identified from satellite gravity data but remain uncharted at fine scale. Seamounts are of particular interest because they can host rich ecosystems. Currents flowing over them can concentrate nutrients, attracting fish and invertebrates. Without detailed maps, understanding their ecological role is incomplete. Abyssal plains, which cover large portions of the ocean floor at depths between about 3,000 and 6,000 meters, may appear featureless at broad scale, but at finer resolution they can contain small ridges, depressions, and sediment structures that influence habitat distribution. Because abyssal plains are so extensive, even a small percentage unmapped translates into enormous physical area. Deep ocean trenches present another challenge. These narrow, elongated depressions often extend thousands of meters below surrounding seafloor. Some trenches have been surveyed in detail, particularly the Mariana Trench. Others remain less thoroughly mapped. Even within well-known trenches, detailed imaging is limited to specific sections visited by submersibles or robotic vehicles. There is also the matter of dynamic processes. The ocean floor is not static over geological timescales. Tectonic activity reshapes it. Submarine landslides alter slopes. Sediment accumulates gradually, covering older structures. Mapping once does not guarantee permanent accuracy. Periodic resurveying is necessary to track changes in certain regions. In addition to physical terrain, the ocean floor hosts human infrastructure. Submarine cables carrying internet traffic cross vast distances. Oil and gas pipelines run along continental margins. In some regions, mineral exploration targets polymetallic nodules scattered across abyssal plains. Understanding where infrastructure lies is important, but it does not equate to comprehensive mapping of surrounding areas. When discussing unexplored ocean floor, it is important to distinguish between unknown and unseen in detail. Scientists have a general understanding of the global distribution of basins and ridges. What is missing in many places is the close-up perspective. Think of it as the difference between knowing that a mountain range exists and having a topographic map showing every contour line, ridge crest, and valley floor. The Seabed 2030 initiative aims to fill these gaps by coordinating international efforts to map the entire ocean floor at high resolution. The goal is ambitious, but reflects recognition that detailed bathymetric data are foundational for many areas of science and policy. Accurate Accurate maps improve tsunami modelling by clarifying how waves interact with seafloor features. They enhance climate models by refining understanding of how currents flow over terrain. They support conservation planning by identifying unique habitats. Despite these motivations, progress remains gradual. Research vessels are finite in number. Survey time competes with other scientific priorities. Some regions are politically sensitive or logistically difficult to access. Weather also limits operations. High seas can delay mapping missions. Remote regions far from ports increase transit time. Even with autonomous vehicles which can operate closer to the seabed and capture finer detail, coverage expands incrementally rather than all at once. There is another dimension to the idea of never seen. Visual exploration of the ocean floor using cameras covers far less area than even high-resolution sonar mapping. Sonar provides topography, but it does not reveal colour, texture, or biological presence in the way video imagery does. Large portions of the seafloor have never been filmed directly. No camera has hovered above them. No light has illuminated their sediments. This is not because they are inaccessible in principle, but because deploying cameras across millions of square kilometres would require extraordinary effort. The ocean floor also contains features that are difficult to detect without close inspection. Cold seeps, small hydrothermal vents, and localised biological communities may go unnoticed in broad surveys. Even with modern technology, discovery often occurs when a vehicle passes over a site for a specific reason and encounters something unexpected. There is also an economic dimension. Regions rich in potential mineral resources such as polymetallic nodules containing manganese, nickel and cobalt have attracted detailed surveys. Other areas without immediate economic interest may remain less thoroughly mapped. This uneven distribution of knowledge reflects practical constraints rather than scientific indifference. When people hear that more of the moon has been mapped in high detail than the ocean floor, they may find it surprising. But mapping the moon does not require dealing with water pressure, storms, or moving currents. Satellites orbiting the moon can scan its surface continuously. In contrast, mapping the ocean floor requires operating from ships on a moving surface, sending sound waves through water, and accounting for variations in temperature and salinity that affect sound speed. The ocean surface also hides the terrain from direct observation. On land, you can walk or fly above a region and see it directly. Underwater, you must rely on indirect sensing or physically descend. Even so, progress continues. Each year, additional swaths of seafloor are mapped in detail. Data are integrated into global databases. International collaborations share resources and expertise. The phrase, "the ocean floor we've never seen," does not imply complete ignorance. It highlights the difference between broad knowledge and detailed familiarity. There are underwater landscapes larger than entire countries that have never been photographed up close. There are sediment plains stretching beyond the horizon of any camera beam. The ocean floor remains one of the least directly observed large environments on Earth, and as mapping improves, attention increasingly turns not just to terrain, but to the midwater regions above it. Because between the surface and the seabed lies another vast zone, the mesopelagic twilight, where light fades and life adapts in ways that are still only partially understood. Between the surface waters we are familiar with and the seafloor we struggle to reach lies a vast region that rarely enters everyday imagination. It is not the shallow coastal zone where coral reefs grow, nor is it the crushing abyss at the very bottom. It is the immense midwater realm where sunlight fades completely and darkness becomes permanent. This region is often called the midnight zone. Technically, it spans from about 1,000 metres below the surface down to roughly 4,000 metres, marking the bathypelagic layer of the ocean. Above it lies the twilight zone, where faint traces of light still penetrate. Below it lie the abyssal plains. But the midnight zone itself occupies an enormous volume of water, far greater than all terrestrial habitats combined. Unlike the ocean floor, which at least offers solid terrain, the midnight zone is open water. There is no bottom in sight, No reference points, no landmarks. It is a three-dimensional expanse of cold, dark water stretching across global ocean basins, and much of it has never been directly observed in detail. When thinking about ocean exploration, people often picture the seabed. But the water column itself, the layers between surface and bottom, holds immense biological complexity. The midnight zone is part of that hidden majority. Temperatures here typically range from about 2 to 4 degrees Celsius. Pressure increases steadily with depth, reaching hundreds of atmospheres. Sunlight does not reach this far down. Any illumination comes from organisms themselves. Bioluminescence becomes the dominant visual phenomenon. Many creatures in the midnight zone produce light through chemical reactions within specialized organs. This light may be blue or green, wavelengths that travel most efficiently through seawater. Some species use flashes of light to startle predators. Others emit steady glows to attract prey. In the absence of sunlight, vision changes meaning. Some organisms have highly sensitive eyes capable of detecting faint bioluminescent signals. Others lose functional eyes entirely and rely on other senses, such as detecting vibrations or chemical cues. The structure of life in the midnight zone differs significantly from surface ecosystems. At the surface, photosynthesis drives food webs. In the midnight zone, energy arrives primarily as falling organic material from above. This slow drift of particles, marine snow, consists of dead plankton, fecal matter, and other debris sinking gradually through the water column. Some organisms migrate vertically to feed. One of the largest daily migrations on Earth occurs within the ocean's midwater layers. Each night, billions of small fish, crustaceans, and other organisms rise toward the surface to feed under cover of darkness. Before dawn, they descend again to deeper waters. This diel vertical migration moves vast quantities of biomass up and down hundreds of meters each day. It plays a significant role in carbon transport, effectively transferring surface-derived carbon into deeper layers. The midnight zone participates in this system, though many of its inhabitants remain at depth continuously. Exploring this region presents unique challenges. Unlike the seafloor, where vehicles can follow terrain, midwater exploration involves navigating in open space. There are no solid features to map visually in the same way. Sonar can detect schools of fish or large objects, but much of the biological life is small and dispersed. Traditional trawling methods have been used to collect specimens, but nets can damage fragile organisms. Some species disintegrate before reaching the surface due to pressure changes. Modern exploration relies on submersibles and ROVs equipped with cameras that can move slowly through midwater. Special care is taken to avoid disturbing organisms with bright lights or propeller wash. Even so, observing delicate gelatinous creatures such as certain jellyfish and siphonophores is difficult. These organisms can be nearly transparent and fragile. Because of these constraints, large areas of the midnight zone have been sampled indirectly rather than observed continuously. Acoustic surveys provide estimates of biomass distribution. Sound waves reflect off dense aggregations of organisms, creating layers detectable on sonar screens. Scientists have identified deep scattering layers, zones where concentrations of organisms reflect sonar signals. These layers often correspond to migrating communities, yet acoustic data reveal presence, not detailed species composition or behaviour. Recent advances in imaging technology have improved observation. High-sensitivity cameras can operate with minimal lighting. Some vehicles use red light, which is less visible to many deep-sea organisms, reducing disturbance. Environmental DNA sampling has also become a valuable tool. By analysing water samples, scientists can detect genetic traces left by organisms in the area, identifying species presence without direct capture. Even with these tools, the midnight zone remains underexplored compared to surface waters. Its scale is immense. It stretches across entire ocean basins, thousands of kilometres wide and several kilometres deep. Covering such volumes systematically would require sustained effort over decades. estimates suggest that the biomass in midwater zones may exceed that of many surface fisheries combined. Lanternfish alone, small bioluminescent fish common in midwater layers, may represent one of the most abundant vertebrate groups on the planet. Yet because they live far below commercial fishing depths and are difficult to access, their ecological role remains only partially understood. The midnight zone also plays a crucial part in global carbon cycling. As organisms feed at the surface and return to depth, they transport carbon downward. When they die at depth, carbon becomes sequestered in deeper waters and sediments. This biological pump influences atmospheric carbon dioxide levels. Understanding it requires knowledge of midwater ecosystems. Despite this importance, funding and public attention often focus more on coral reefs or charismatic surface species. The midnight zone, invisible and remote, receives less spotlight. Still, scientific interest continues to grow. Some research programs now target mesopelagic and bathypelagic zones specifically, aiming to quantify biomass and species diversity more accurately. Improved acoustic methods and machine learning algorithms help classify organisms detected by sonar. Deep-sea observatories occasionally include midwater sensors to track movement patterns over time. One reason this region remains less explored is the difficulty of staying in one place within it. Unlike the seafloor, where a vehicle can rest or anchor, midwater vehicles must actively maintain position. Currents can shift them. Precise navigation becomes more complex. In addition, midwater organisms often move continuously. Capturing representative samples requires careful timing and positioning. There is also the issue of scale perception. Because the midnight zone lacks visible landmarks, it is harder to conceptualize. When thinking of the ocean floor, one can imagine mountains and plains. Midwater is less intuitive, a vast, dark space filled with moving life. It is easy to overlook simply because it does not resemble familiar terrestrial environments, and yet, in terms of sheer volume, it represents one of the largest habitats on Earth. If the goal is to assess how much of the ocean we have truly explored, the midnight zone must be considered separately from both surface waters and seabed. Surface layers are monitored extensively by satellites and ships. The seabed is increasingly mapped in high resolution, though incompletely. The midwater layers remain more sparsely sampled, particularly at greater depths. No global, high-resolution biological survey of the midnight zone exists. Observations are pieced together from expeditions targeting specific regions. This does not mean that scientists are unaware of its existence or structure. It means that detailed, continuous observation across its full extent remains impractical. The ocean's vertical dimension adds complexity to exploration statistics. Even if the entire seafloor were mapped in detail, vast water volumes above it would still require separate study. In many ways, the midnight zone exemplifies the challenge of ocean exploration. It is physically accessible with modern technology, yet so expansive that coverage accumulates slowly. Understanding it fully would require coordinated, sustained missions across global basins. As exploration continues, attention shifts from merely confirming that life exists in darkness to understanding its scale, interactions, and impact on planetary systems. Because the midnight zone is not an isolated curiosity. It is part of a continuous ocean system connecting surface productivity to deep-sea stability, and beyond it, even deeper, lie the trenches where pressure intensifies further and ecosystems become even more specialized. Those regions at the margins of tectonic plates represent some of the least visited places on Earth. At the edges of tectonic plates, where one slab of Earth's crust bends and slides beneath another, the ocean floor drops sharply into narrow, elongated depressions. These are the trenches. They are the deepest parts of the ocean, extending far below the surrounding seabed, reaching depths that exceed the height of Mount Everest if it were placed upside down. The most well-known is the Mariana Trench in the western Pacific Ocean. Its deepest point, Challenger Deep, descends to nearly 11,000 meters below sea level. But the Mariana is not alone. Trenches line portions of the Pacific Rim, including the Tonga Trench, the Philippine Trench, and others scattered across ocean basins. These regions occupy a small percentage of total ocean area compared to abyssal plains, yet they represent the extreme limit of marine environments. Pressure in trenches exceeds 1,000 atmospheres. Temperatures remain just above freezing. Sunlight is entirely absent. The terrain is steep and unstable, shaped by tectonic forces and sediment flows. For decades, trenches were assumed to be nearly devoid of life. The combination of pressure, cold, and isolation seemed prohibitive, but exploration has revealed otherwise. In 1960, when the bathyscaphe Trieste descended to Challenger Deep, observers reported seeing what appeared to be a flatfish on the seafloor. Later analysis questioned that observation, suggesting it may have been a different type of organism. Regardless, the descent demonstrated that the trench floor was not barren rock. Subsequent expeditions using remotely operated vehicles and deep-rated submersibles have documented life in trench environments. Amphipods, small shrimp-like crustaceans, are among the most common trench inhabitants. They scavenge organic material that drifts downward from upper layers. Some species have been observed at depths exceeding 10,000 meters. Snailfish, delicate gelatinous fish adapted to extreme pressure, have also been recorded near trench floors. These fish possess reduced bone density and soft bodies that tolerate compression. Their physiology includes specialized molecules that stabilize proteins under high pressure. One of the most striking aspects of trench life is adaptation at the molecular level. Under extreme pressure, biological molecules can behave differently. Proteins may lose shape, membranes may become too rigid. Trench organisms produce compounds that counteract these effects. Trimethylamine N-oxide, or TMAO, is one such molecule. It helps stabilize proteins under pressure, allowing normal cellular function. As depth increases, concentrations of TMAO in organisms also increase, up to a limit beyond which further adaptation becomes biochemically impractical. This may explain why fish are not found beyond certain trench depths. The biochemical cost of maintaining stability becomes too high. Microbial life also thrives in trenches. Bacteria and archaea inhabit sediments, metabolizing organic material and participating in nutrient cycles. Some microbes are adapted to high pressure in ways that differ significantly from surface relatives. Trenches receive organic input from above, but because they are narrow and often act as sediment traps, material can accumulate. This makes them focal points for scavengers. Yet trench ecosystems are not simply deeper versions of abyssal plains. Their steep walls and confined structure create distinct environmental conditions. Currents behave differently. Sediment movement can be more dynamic. Exploration of trenches remains limited compared to other deep-sea regions. Descending to nearly 11,000 meters requires specialized vehicles rated for extreme pressure. Only a small number of submersibles worldwide are capable of reaching such depths. Each descent involves careful engineering and significant cost. Equipment must withstand crushing force. Communication with surface vessels relies on acoustic systems with limited bandwidth. Because missions are rare, trench observations are episodic rather than continuous. This means that while we know life exists in trenches, we do not have comprehensive surveys of species diversity across all trench systems. Some trenches have been visited multiple times, others have been visited rarely or not at all in modern expeditions. Sampling organisms at such depths presents additional challenges. Bringing specimens to the surface without decompression damage is difficult. Specialized pressure-retaining chambers are sometimes used, but they add complexity to missions. Despite these constraints, discoveries continue. In recent years, plastic debris has been found even in trench environments. Amphipods sampled from deep trenches have contained microplastics in their digestive systems. This finding highlights how human activity affects even the most remote ocean regions. Chemical pollutants have also been detected in trench sediments, carried downward through marine snow and sinking debris. The presence of anthropogenic material in trenches underscores their connection to global systems. They are not isolated pockets beyond human influence. Geologically, trenches play a critical role in plate tectonics. They mark subduction zones where oceanic crust descends into the mantle. Earthquakes and volcanic activity often occur near these boundaries. Studying trench environments helps scientists understand tectonic processes and seismic risk. From a biological perspective, trenches may host species unique to specific systems. Geographic isolation can promote endemism, meaning species found in one trench may not occur elsewhere. However, because detailed surveys are limited, the extent of trench biodiversity remains uncertain. When people hear that only a small percentage of the ocean has been explored, trenches represent part of that uncertainty. Their extreme depth and narrow structure make them difficult to study comprehensively. Compared to the broad abyssal plains, trenches occupy less area, but in terms of exploration frequency and detailed observation, they are among the least visited environments on Earth. There have been fewer human visits to the deepest trenches than there have been human landings on the Moon. This comparison highlights both the difficulty and rarity of direct trench exploration. Yet robotic systems have expanded access. Deep-rated ROVs and AUVs continue to collect imagery and data. As technology improves, missions to trenches may become more common. New materials, better pressure-resistant housings, and improved navigation systems reduce risk. Still, the scale of the task remains large. There are dozens of major trench systems worldwide. Mapping and biologically surveying each in detail would require sustained effort over many years. The creatures of the trenches illustrate how life adapts to extreme conditions. They demonstrate that even the most inhospitable seeming environments can host ecosystems. At the same time, their relative obscurity highlights the limits of exploration. We have glimpsed trench life through specific missions, but continuous high-resolution observation across all trench systems remains incomplete. Understanding trench ecosystems also informs broader questions about biodiversity and resilience. Extreme environments can reveal biological strategies not visible elsewhere. As exploration continues, trenches serve as both a frontier and a reminder of the ocean's vertical reach. Beyond trenches, other hidden landscapes lie beneath the waves: submerged mountains, volcanic arcs, and even remnants of ancient human settlements now underwater due to sea level rise. These features add further complexity to what remains unseen, and each new descent into the depths adds a small piece to a picture that is still far from complete. If light disappears quickly beneath the surface, sound does not. In fact, sound becomes the primary way we sense the deep ocean at all. Human vision is limited underwater. Even in clear tropical seas, visibility fades with depth. In the deep ocean, darkness is complete. But sound travels through water efficiently and over long distances. While light is absorbed and scattered, sound waves can cross entire ocean basins under the right conditions. Because of this, much of what we know about the deep ocean has come not from seeing it, but from hearing it. The use of sound in ocean exploration began as a practical solution to a simple problem. How deep is the water beneath a ship? Early echo-sounding systems sent a pulse of sound downward and measured the time it took for the echo to return. Knowing the speed of sound in water, scientists could calculate depth with far greater efficiency than lowering weighted lines. Over time, this basic principle evolved into sophisticated multi-beam sonar systems capable of mapping wide swathes of seafloor in remarkable detail. Multi-beam sonar works by emitting a fan-shaped array of sound pulses beneath a vessel. Instead of a single beam pointing straight down, multiple beams spread outward, covering a broad area of the seabed. Each returning echo is timed precisely. The result is a detailed bathymetric map. As ships travel back and forth across an area in parallel lines, overlapping swaths build a three-dimensional model of the terrain below. Without sonar, mapping the ocean floor at scale would be nearly impossible. it would require countless individual depth measurements taken manually. With sonar, vast areas can be surveyed systematically. Yet sonar does more than map terrain. It reveals movement. When sound waves encounter objects in the water column, schools of fish, dense layers of plankton, or even large marine mammals, they reflect differently. Scientists began noticing persistent bands in sonar readings, known as deep scattering layers. These layers corresponded to concentrations of organisms in midwater zones. This discovery was significant. It meant that sound could detect biological patterns invisible to the eye. The ocean also has a natural acoustic structure shaped by temperature and pressure gradients. Sound speed in water depends on temperature, salinity, and pressure. Near the surface, warmer water allows sound to travel faster. As depth increases and temperature drops, sound speed decreases. Deeper still, increasing pressure raises sound speed again. This creates a minimum sound speed layer at a certain depth, often around 1,000 meters, depending on location. Sound waves entering this layer can become trapped, traveling horizontally for long distances with minimal loss of energy. This phenomenon is known as the SOFAR channel, short for sound fixing and ranging. During the mid-20th century, researchers discovered that low-frequency sounds could travel thousands of kilometers through this channel. Explosions, earthquakes, and even whale calls could be detected far from their source. Institutions such as Woods Hole Oceanographic Institution contributed significantly to understanding underwater acoustics, studying how sound moves through varying ocean conditions. The SOFAR channel allowed scientists to monitor seismic activity beneath the sea. It also became important in military applications such as submarine detection during the Cold War. Beyond mapping and detection, sound is central to marine life itself. In the deep ocean, where light is absent, many organisms rely on sound for communication and navigation. Marine mammals, such as whales, produce low-frequency calls that can travel across entire ocean basins. Blue whales emit calls that may be heard hundreds or even thousands of kilometers away under favorable conditions. These vocalizations serve purposes ranging from mating communication to navigation. To study whale populations, researchers deploy hydrophones, underwater microphones that record acoustic signals over long periods. These devices reveal migration patterns and behavioral changes without requiring constant visual observation. Sound also allows scientists to detect geological processes. Underwater volcanic eruptions, landslides, and tectonic movements produce acoustic signatures. By analysing these sounds, researchers can identify events occurring in remote regions without direct visual confirmation. For example, activity near the Mariana Trench has been monitored acoustically to study tectonic dynamics. Acoustic methods extend even further. Active sonar systems emit sound pulses and analyse their reflections. Passive systems simply listen. Passive acoustic monitoring has become an important tool for understanding human impact as well. Ship traffic generates continuous low-frequency noise. Industrial activities contribute additional sound pollution. Studies show that increased ocean noise can affect marine mammals, interfering with communication and navigation. As ocean traffic grows, acoustic environments shift. The soundscape of the ocean is therefore both natural and anthropogenic. In exploring how much of the ocean we have truly explored, acoustic mapping accounts for a large share of our knowledge. Much of the global bathymetric dataset is built on sound-based measurements, but there is a difference between detecting shape and experiencing place. Sonar can outline a seamount rising from the abyssal plain. It can measure its height and slope, but it cannot reveal the species living on its rocky surfaces without additional imaging. Similarly, acoustic surveys can estimate biomass in mid-water layers, but distinguishing between species often requires visual confirmation or physical sampling. Sound provides structure, vision provides detail. Even with high-resolution multi-beam sonar, resolution depends on altitude above the seabed and beam frequency. Higher frequencies offer finer detail, but attenuate more quickly, limiting range. Lower frequencies travel farther but produce coarser images. Choosing appropriate settings involves balancing coverage and precision. There are also regions where acoustic mapping is sparse. Remote areas far from major shipping routes or research hubs may have fewer survey lines. While satellite altimetry provides a global outline, it lacks the resolution to detect smaller features such as small seamounts or localized ridges. Thousands of such features likely remain undetected or only vaguely inferred. In addition, acoustic surveys require calibration. Sound speed varies with temperature and salinity. Without accurate profiles of these properties, depth calculations can be slightly off. Oceanographers deploy CTD instruments, measuring conductivity, temperature, and depth to refine sound speed models during mapping missions. Despite its limitations, sound remains the most effective way to map and monitor the deep ocean at scale. It allows coverage of terrain that cannot be seen directly. It reveals moving layers of life. It tracks geological events in real time. Yet reliance on sound also highlights what remains unseen. An acoustic map of a trench may show steep walls and a narrow floor, but only a camera descent reveals sediment type, biological presence, or subtle structural details. In some cases, acoustic surveys have revealed unexpected features, previously unknown seamount chains, hidden fracture zones, or submerged volcanic cones. Each discovery emphasizes how much remains beneath the surface, undetected until sound waves pass over it. There is also an emotional dimension to underwater acoustics. Recordings from hydrophones capture the ambient hum of the ocean, distant whale songs, crackling shrimp colonies, the faint rumble of shifting tectonic plates. For researchers, listening becomes a form of exploration. Unlike visual images, which capture specific scenes, soundscapes record activity across space and time. They reveal patterns invisible to the eye. In remote regions where sending submersibles is costly, long-term acoustic monitoring offers a more practical alternative. As technology advances, machine learning algorithms assist in analysing vast acoustic datasets. Automated systems identify whale calls, detect unusual signals, and classify patterns more efficiently than manual review. This combination of sound and computation expands our ability to monitor large areas continuously. Still, the acoustic map of the ocean remains incomplete. There are regions with limited survey coverage. There are deep basins where detailed multi-beam mapping has yet to occur. There are midwater zones where biological composition is estimated rather than fully catalogued. Sound provides a broad framework of knowledge, but within that framework many details await closer examination. When we say that much of the ocean remains unexplored, part of what we mean is that we have heard its outlines but not yet seen its full complexity. And beyond geological formations and biological layers, the ocean hides remnants of human history, shipwrecks, submerged settlements, and traces of past civilizations now resting beneath shifting sediments. Those hidden structures represent another dimension of exploration, one that intersects archaeology, geology, and marine science, extending the question of what lies beneath beyond natural processes alone. When we think about unexplored parts of the ocean, it is easy to picture untouched seafloor and unfamiliar species. But not everything hidden beneath the waves is natural. Some of it once stood in sunlight. Some of it was built by human hands. Some of it carried passengers, cargo, entire communities, before disappearing below the surface. The ocean does not only conceal geological landscapes and deep-sea organisms, it also holds history. Across the world's seas lie shipwrecks, submerged cities, aircraft, harbours, and traces of civilizations that existed long before modern coastlines took their current shape. In many cases, these sites remain only partially explored. Some have been mapped broadly, others have been visited briefly by submersibles, many have yet to be located at all. The number of shipwrecks alone is staggering. Estimates suggest that more than 3 million wrecks may rest on the ocean floor worldwide. only a small fraction of these have been identified or surveyed in detail. One of the most well-known examples is the wreck of the RMS Titanic. The Titanic lies about 3,800 metres below the surface of the North Atlantic Ocean. Discovered in 1985, its bow and stern sections rest separated by a debris field. Despite decades of study, the site continues to change as corrosion and biological activity slowly break down the structure. Exploring the Titanic required deep-sea technology capable of withstanding significant pressure. Even now, visits to the wreck are limited and costly. Large portions of the debris field remain only partially documented. But the Titanic is only one example, and a relatively well-known one. Far older remains lie beneath coastal waters. Sea levels have not always been where they are today. During the last glacial maximum, around 20,000 years ago, sea levels were more than 100 metres lower than today. As ice sheets melted, rising seas flooded coastal plains, river valleys, and human settlements. This means that prehistoric sites now lie underwater. In the Mediterranean, the ancient Egyptian port city of Thonis Herakleion was rediscovered in 2000 beneath Abu Qir Bay. Once a major trading hub, it sank gradually due to soil liquefaction and subsidence, eventually disappearing beneath the sea. Underwater excavations revealed temples, statues, ships, and everyday objects preserved in sediment. For centuries, Thonis Herakleion was known only from written sources. Its rediscovery demonstrated how entire cities can vanish beneath shifting coastlines. Similar submerged settlements have been identified in other regions, including parts of the Black Sea and off the coasts of India and Japan. In some cases, sonar surveys have detected regular structures consistent with human construction. Further exploration is often slow and methodical. Underwater archaeology presents challenges distinct from terrestrial excavation. Visibility can be limited. Currents complicate work. Equipment must function underwater for extended periods. Objects must be stabilized carefully to prevent damage during recovery. At greater depths, human divers cannot operate safely. Remotely operated vehicles become essential. In the Black Sea, anoxic conditions, waters lacking oxygen below certain depths, have preserved wooden shipwrecks in remarkable condition. The Black Sea Maritime Archaeology Project has documented ships from ancient Greek, Roman and Ottoman periods resting upright on the seafloor, with masts and rudders intact. Because oxygen-consuming organisms cannot survive in those layers, decay proceeds slowly. These wrecks offer rare glimpses into shipbuilding techniques from centuries ago. Yet even in such well-documented cases, only selected sites have been surveyed in detail. Vast stretches of the Black Sea floor remain unexamined at high resolution. Shipwrecks are not distributed evenly. Trade routes, wartime activity, and storm patterns influence where vessels sank. Many likely lie buried beneath sediment, undetected by sonar until specific surveys are conducted. Modern multi-beam sonar and side-scan sonar systems have improved wreck detection. Side-scan sonar in particular produces detailed images of objects lying on the seabed by measuring reflected sound intensity. But identifying a sonar anomaly as a specific wreck requires further investigation. Deploying ROVs, or divers, to confirm identity takes time and resources. Beyond ships and cities, aircraft lost during conflicts have also been located in deep waters. Some remain undiscovered. Others have been documented only recently as technology improved. In certain regions, wartime debris fields cover large areas. The Pacific Ocean, for example, contains numerous shipwrecks and aircraft remains from World War II. Some lie at depths beyond recreational diving limits, requiring technical diving or robotic exploration. There is also the issue of preservation. Salt water is corrosive. Metal structures degrade over time. Wood is consumed by organisms in oxygenated waters. Sediment burial can both protect and obscure remains. In deep waters, low temperatures and reduced biological activity can slow decay, but chemical processes continue. exploration of submerged human history often intersects with ethical and legal considerations. Shipwrecks may be war graves. Ownership rights can be contested. Salvage operations raise questions about cultural heritage preservation. International conventions, such as UNESCO's Convention on the Protection of the Underwater Cultural Heritage, aim to regulate activities and protect sites from looting or destruction. The ocean's ability to conceal history adds another dimension to the question of exploration. It is not only natural terrain that remains unseen. Human narratives are also scattered across seabeds. In some cases, underwater discoveries reshape historical understanding. Shipwreck cargoes reveal trade networks. Submerged settlements challenge timelines of coastal occupation. Yet compared to terrestrial archaeology, underwater archaeology covers only a fraction of potential sites. The challenge is partly logistical. Oceans cover far greater area than land. Surveying even coastal shelves systematically would require enormous effort. Technology continues to improve detection capabilities. Autonomous vehicles equipped with high-resolution sonar can scan large areas more efficiently than earlier systems. Artificial intelligence assists in identifying patterns in sonar data, flagging potential wreck sites for further investigation. Still, coverage accumulates gradually. When we consider how much of the ocean has been explored, cultural heritage sites form a significant part of what remains hidden. For every famous wreck documented, countless others lie undiscovered. For every submerged city rediscovered, many more prehistoric settlements likely rest beneath continental shelves. Even modern infrastructure contributes to this layered history. Discarded fishing gear, lost shipping containers, and other debris accumulate on the seafloor. Some of these items become integrated into marine ecosystems over time. The ocean becomes both archive and environment. It is important to distinguish between known unknowns and unknown unknowns. In some cases, historical records indicate ships lost in specific storms or battles. Researchers know roughly where to search. In other cases, no record exists. A vessel may have vanished centuries ago without documentation. Similarly, ancient coastal settlements may have left no written trace. Only geological and sonar surveys might reveal their presence. As mapping improves, discoveries will likely increase. But given the scale of continental shelves and deep basins, comprehensive identification of all submerged human sites is improbable in the near term. The ocean's capacity to preserve and conceal human history underscores how incomplete exploration remains. We have charted many coastlines. We have identified major wrecks and notable submerged cities, but beneath the surface, across vast areas, lie artifacts and structures no one has seen since they sank. Exploring these sites requires balancing scientific curiosity with preservation ethics. It requires technology capable of operating at depth. It requires sustained funding and interdisciplinary collaboration. And beyond human history, the ocean floor also preserves geological records that influence global systems. Sediment layers archive past climate conditions. Chemical signatures record volcanic events. Understanding these records connects ocean exploration to climate science. Lost worlds beneath the waves are not only remnants of ships and cities, they are layers of natural and human history intertwined. As exploration continues, attention shifts not only to what rests on the seafloor, but to how the ocean itself shapes planetary processes. Because while submerged ruins capture imagination, the ocean's largest hidden role lies in regulating climate, absorbing heat, and cycling carbon. And much of that influence operates quietly, in depths and layers still only partially measured. When people think about climate, they often picture the atmosphere first, clouds moving across continents, carbon dioxide rising from factories and vehicles, storm systems forming and dissipating over land. The sky feels like the stage where climate unfolds, but the ocean is not just part of that system. It is the largest active component within it. The ocean stores heat, absorbs carbon dioxide, drives circulation patterns that redistribute energy around the planet, and influences rainfall across entire continents. Without it, Earth's climate would be radically different. Understanding how much of the ocean we have explored includes understanding how much we know about its role in climate. And while scientists have made significant progress, much of that understanding comes from indirect measurement and modelling rather than comprehensive, high-resolution observation of every layer. Start with heat. Water has a high heat capacity. It can absorb large amounts of heat energy without changing temperature as quickly as air. Because the ocean covers more than 70% of Earth's surface, it acts as a massive thermal reservoir. As greenhouse gases trap heat in the atmosphere, much of that excess heat does not remain in the air. It is absorbed by the ocean. Measurements show that over 90% of the excess heat trapped by greenhouse gases in recent decades has gone into the ocean. Surface waters warm first, but heat gradually penetrates deeper layers through mixing and circulation. To measure this, scientists rely on a combination of tools. Satellites track sea surface temperature globally. These data provide near-continuous coverage of the uppermost layer. But surface temperature is only part of the story. Below the surface, temperature profiles are measured using instruments such as Argo floats. The Argo program deploys thousands of autonomous floats across the world's oceans. Each float drifts at depth, periodically descending and ascending while measuring temperature and salinity. When it reaches the surface, it transmits data via satellite. The global Argo array provides a broad picture of upper and mid-depth ocean conditions. It is one of the most important climate monitoring systems in operation. Yet Argo floats typically operate down to about 2,000 meters. Deeper layers, including much of the abyssal plain, are less densely monitored. Some deep Argo floats now extend measurement to 4,000 or even 6,000 meters, but coverage is not uniform. This means that while we know the ocean is absorbing heat, the exact distribution of that heat at extreme depths remains less precisely mapped than surface trends. Heat distribution is linked to ocean circulation. Surface currents, driven by wind and Earth's rotation, move warm water from the tropics toward higher latitudes. The Gulf Stream in the North Atlantic, for example, carries warm water northward, influencing climate in Europe. Beneath surface currents lies a deeper circulation system, driven by differences in water density. Colder, saltier water sinks in certain regions, such as the North Atlantic and around Antarctica, forming deep water masses that flow through global basins. This system is often referred to as thermohaline circulation. Understanding its behaviour requires tracking temperature and salinity patterns across vast distances and depths. Scientists use ship-based surveys, moored instruments, floats, and satellites to piece together circulation patterns. But the system is complex and dynamic. It varies seasonally and over longer timescales. Climate models incorporate ocean circulation to predict future warming patterns. If deep water formation slows or shifts due to changing temperatures or freshwater input from melting ice, regional climates could change significantly. The ocean also plays a central role in the carbon cycle. Carbon dioxide from the atmosphere dissolves in surface waters. Some of this dissolved carbon is used by phytoplankton during photosynthesis. When these organisms die, a portion of the carbon sinks into deeper layers as marine snow. This process, known as the biological pump, transfers carbon from the atmosphere into the deep ocean, where it can remain for centuries or longer. Forms allow the ocean to store large amounts of carbon. However, increased carbon dioxide absorption leads to ocean acidification. As more CO2 dissolves, seawater pH decreases slightly. While the change may seem small numerically, it can affect organisms that rely on calcium carbonate to build shells and skeletons, such as corals and some plankton. Monitoring ocean acidification requires careful chemical measurement across different depths and regions. Surface waters are relatively well sampled. Coastal areas often receive more attention due to ecological and economic importance. Deep waters are less frequently sampled, particularly in remote basins. This uneven coverage reflects practical constraints rather than lack of awareness. Climate influence extends beyond temperature and carbon. The ocean regulates rainfall patterns through evaporation. Warm surface waters in tropical regions fuel atmospheric convection, driving monsoons and storm systems. El Niño and La Niña events in the Pacific Ocean arise from shifts in surface temperature and circulation patterns. These events influence weather globally, affecting agriculture, water supply, and storm frequency. Detecting and predicting such events requires continuous monitoring of ocean conditions across large regions. Buoy networks such as the Tropical Atmosphere Ocean Array provide real-time data on temperature and wind in the equatorial Pacific. Satellites complement these measurements. Still, predicting the precise evolution of climate patterns remains challenging, because ocean-atmosphere interactions are complex. The deeper ocean acts as a long-term memory within the climate system. Surface conditions may fluctuate seasonally, but deep waters change more slowly. Heat and carbon absorbed at the surface may take decades or centuries to circulate through deep basins. This delayed response complicates climate projections. Even if greenhouse gas emissions were reduced significantly, stored heat in the ocean would continue influencing climate for some time. Understanding how quickly deep waters mix and circulate is therefore critical, yet direct measurement at extreme depths remains less comprehensive than at the surface. There are also regions that are undersampled due to logistical challenges. The Southern Ocean surrounding Antarctica plays a major role in deep water formation and carbon uptake. Harsh weather and remote location limit the frequency of surveys. Efforts to improve monitoring include deploying ice-capable floats and moorings, but gaps remain. When discussing how much of the ocean we have explored, it is important to recognize that exploration includes measurement of physical and chemical properties, not just visual mapping. In terms of climate-related variables, the ocean is better monitored now than at any time in history. Satellite networks provide global surface coverage. Thousands of floats gather subsurface data. Yet full, high-resolution coverage across all depths and regions is not yet achieved. The ocean's role in climate underscores why exploration matters beyond curiosity. Accurate bathymetric maps improve climate models by refining how currents interact with terrain. Better understanding of midwater ecosystems informs estimates of carbon sequestration. Knowledge of trench and abyssal processes may reveal additional pathways of nutrient cycling. The ocean is not simply a passive absorber of heat and carbon. It is an active regulator. Exploring it fully would mean not only mapping its terrain, but measuring its temperature, chemistry, and biological processes across all layers consistently. While significant progress has been made, especially in surface and upper layer monitoring, the deeper and more remote parts of the ocean remain less densely observed. And beyond physical and chemical processes, there is another layer of life that plays a critical role in climate regulation: microbial communities invisible to the naked eye. These microscopic organisms drive many of the chemical transformations occurring in seawater, and much of their diversity remains only partially understood. To grasp how complete our exploration truly is, we must look not only at visible creatures and physical landscapes, but at the microscopic worlds within the ocean that influence planetary systems on scales far larger than their size suggests. When people imagine unexplored parts of the ocean, they often picture vast seafloor plains or deep trenches. They imagine creatures with bioluminescent lures or unusual body shapes moving through darkness. But there is another layer of the ocean that is just as expansive and far less visible. It exists in every drop of seawater. The ocean is not only a large physical space, it is also a microscopic universe. Within a single milliliter of seawater, there can be millions of microbial cells. Bacteria, archaea, viruses, and microscopic eukaryotes form complex communities that drive many of the ocean's most important processes. These microbial systems are sometimes described as micro-oceans within because of their scale and influence. They are invisible to the naked eye, yet they shape chemistry, climate, and the flow of energy through marine ecosystems. Exploring the ocean at the microbial level presents challenges different from mapping terrain or filming deep-sea organisms. It requires chemical analysis, genetic sequencing, and careful sampling techniques. For much of scientific history, microbes were underestimated in ocean studies. Early oceanography focused on visible organisms and physical measurements such as temperature and salinity. Plankton was studied, but mainly those large enough to be captured in nets. It was not until advances in microscopy and molecular biology that the true abundance and diversity of marine microbes became clear. In the late 20th century, researchers began using genetic tools to identify microorganisms that could not be cultured in laboratory conditions. By extracting DNA directly from seawater samples, scientists discovered entirely new groups of microbes that had never been grown in petri dishes. One landmark discovery was the identification of abundant photosynthetic bacteria known as Prochlorococcus. These tiny organisms are among the most numerous photosynthetic cells on Earth. They inhabit surface waters and contribute significantly to global oxygen production and carbon fixation. Without them, atmospheric composition and climate would differ. Beyond surface layers, microbial communities change with depth. In the twilight and midnight zones, where sunlight does not reach, microbes rely on alternative energy sources. Some consume organic matter sinking from above. Others perform chemosynthesis near hydrothermal vents, converting chemicals such as hydrogen sulfide into energy. In deep-sea sediments, microbial life persists even kilometers beneath the ocean floor. These organisms metabolize slowly, surviving on limited chemical gradients. Some may divide only once every several years. The deep biosphere, as it is sometimes called, represents one of the least explored habitats on Earth. Sampling these environments requires specialized drilling equipment and sterile techniques to avoid contamination. Core samples extracted from the seabed must be handled carefully to preserve pressure-sensitive organisms. Even with modern methods, identifying microbial species remains complex. Many microbes share similar physical characteristics but differ genetically. Sequencing technologies allow classification based on genetic markers, revealing diversity far beyond what was once imagined. Viruses also play a significant role. Marine viruses infect bacteria and plankton, influencing population dynamics and nutrient cycling. When viruses lyse host cells, they release organic material back into the water, affecting carbon flow. This viral shunt redirects energy pathways within marine food webs. In surface waters, phytoplankton form the base of many food chains. They convert carbon dioxide into organic matter through photosynthesis. Microbes interact closely with these phytoplankton, recycling nutrients and influencing bloom dynamics. Harmful algal blooms, for example, can be shaped by microbial interactions and nutrient availability. Because microbes are so small and numerous, mapping their distribution requires sampling across many locations and depths. Large research programs have undertaken global expeditions to catalogue microbial diversity. The Tara Oceans expedition, for instance, collected samples across multiple ocean basins to analyse planktonic and microbial communities. These efforts have expanded knowledge significantly, but coverage remains incomplete. Microbial communities vary not only with depth, but also with temperature, salinity, nutrient levels, and regional circulation patterns. Polar oceans host different assemblages than tropical waters. Coastal zones differ from open ocean gyres. Seasonal changes also influence composition. In temperate regions, spring blooms alter nutrient dynamics and microbial populations. Monitoring these patterns continuously across the entire ocean would require extensive sampling networks. Automated samplers and in situ genetic sensors are under development, but they're not yet deployed at global scale. Another complexity is functional diversity. Identifying which microbes are present is only part of the task. Understanding what they are doing, what metabolic pathways they use, how they respond to environmental change is equally important. Microbes mediate nitrogen cycling, converting nitrogen between forms usable by different organisms. They influence sulfur and phosphorus cycles. They contribute to methane production and consumption. These chemical transformations affect greenhouse gas concentrations and nutrient availability. In the context of climate, microbial processes are essential. The biological pump that transfers carbon from surface waters to depth depends heavily on microbial decomposition. When organic matter sinks, microbes break it down, releasing carbon dioxide back into the water column or locking it into sediments. The balance between these processes influences how much carbon remains stored in deep waters versus returning to the atmosphere. Ocean acidification also affects microbial communities. Changes in pH can alter enzyme activity and community composition. Yet predicting these changes requires more detailed understanding of microbial ecology than currently available. Because microbes are microscopic and widely distributed, their exploration does not depend on deep-sea submersibles in the same way trench organisms do. Instead, it depends on laboratory analysis and advanced sequencing technologies. This means that in some respects, microbial exploration can progress faster than mapping remote seafloor terrain. However, challenges remain. Collecting representative samples from extreme depths is logistically demanding. Maintaining in situ pressure conditions during retrieval is difficult. Some microbes may not survive decompression, altering observed community composition. In addition, interpreting genetic data requires sophisticated computational tools. Sequencing generates enormous datasets that must be analysed carefully. Despite these obstacles, knowledge of marine microbial diversity has expanded dramatically over the past few decades. Even so, scientists estimate that many marine microbial species remain undiscovered or poorly characterised. When considering how much of the ocean we have explored, microbial life adds another layer of uncertainty. We may have broad maps of basins and ridges. We may have documented charismatic deep-sea species. But within each litre of seawater lies a complex community that is still being catalogued. The ocean is not just a physical space. It is a biochemical engine powered largely by microscopic organisms. Understanding this engine fully requires continued sampling across depths and regions, integration of genetic data, and long-term monitoring of community shifts. As exploration technology advances, integrating microbial data with physical and chemical measurements becomes increasingly important. Because the ocean's role in climate, nutrient cycling, and ecosystem stability depends heavily on processes occurring at scales invisible to human eyes, and while mapping seafloor terrain may seem like the primary frontier, understanding these micro-oceans within may prove just as critical in determining how complete our exploration truly is. From here, a broader comparison emerges. Given the challenges of mapping terrain, studying midwater ecosystems, and cataloguing microbial diversity, it becomes natural to ask why exploration progresses at its current pace. And that leads to a comparison often made in public discussions. Why does it sometimes feel as though we know more about distant planets than about our own ocean? It is a comparison that appears often in conversations about the ocean. People point out that humans have walked on the moon. Robotic spacecraft have travelled to Mars, Jupiter and beyond. Detailed maps of planetary surfaces millions of kilometres away exist, and yet large portions of our own ocean floor remain mapped only in broad outline. The question seems straightforward. Why does it sometimes feel as though exploring space has progressed faster than exploring the deep ocean? The answer is not that space is easier in an absolute sense. Space presents its own extreme challenges: vacuum, radiation, temperature swings. But the environments differ in ways that make certain aspects of exploration more practical in orbit than beneath the sea. Start with visibility. When a spacecraft orbits the Moon or Mars, it can use cameras and radar to map the surface directly from above. There is no intervening medium like water blocking visibility. Light reflects from the surface and travels through near vacuum to the instrument. Underwater, light does not travel far. After only a few hundred meters, sunlight disappears entirely. Even artificial light illuminates only a small area around a submersible. There is no way to place a camera in orbit around the Earth and see the ocean floor directly through kilometers of water. Water absorbs and scatters electromagnetic radiation. Radio waves, which are used extensively in space communication and radar mapping, do not travel effectively through seawater. This limits remote sensing options. In space exploration, orbiters can circle a planet repeatedly, scanning large areas efficiently. The Mars Reconnaissance Orbiter, for example, has mapped the Martian surface in high resolution from orbit for years. By contrast, mapping the ocean floor requires ships travelling across the surface, sending sound waves downward. Each survey vessel covers a relatively narrow swathe at a time. To achieve full coverage, ships must trace systematic paths across vast areas. The ocean covers about 361 million square kilometres. That is more than twice the surface area of Mars. Mapping that area at high resolution using ship-based sonar is inherently time-consuming. There is also the issue of stability. A spacecraft in orbit moves predictably according to well-understood gravitational mechanics. Once launched, it does not face storms or shifting currents. It does not require fuel for station keeping in the same way a ship must counteract wind and waves. Research vessels operating at sea contend with weather systems, waves, and mechanical wear. Storms can delay missions. Rough seas complicate deployment of deep-sea vehicles. Operating in space is technologically complex, but the environment does not corrode equipment the way saltwater does. Saltwater is highly corrosive. It degrades metal, damages electronics, and requires constant maintenance. Pressure is another factor. In space, the challenge is keeping pressure inside a spacecraft. In the deep ocean, the challenge is resisting immense external pressure. Designing a vessel that can withstand 1,000 atmospheres of pressure is a significant engineering task. Materials must be thick, strong, and precisely manufactured. Any structural weakness can be catastrophic. In orbit, a spacecraft does not experience crushing force from its environment. It must contain internal pressure for human crews, but robotic spacecraft often operate in vacuum without such constraints. Communication also differs. Spacecraft communicate using radio waves that travel effectively through space. High bandwidth data can be transmitted over long distances with appropriate antenna systems. Underwater, communication relies largely on acoustic signals. These have lower bandwidth and slower data transfer rates. Real-time video from deep-sea vehicles is possible through tethers, but untethered systems must store data and transmit limited updates acoustically. This affects operational flexibility. In space, a rover on Mars can send images back regularly. In the deep ocean, an autonomous vehicle may complete its mission and only then transmit its full dataset upon resurfacing. Funding and public perception also influence pace. Space exploration has long captured public imagination. It carries symbolic and geopolitical significance. During the 20th century, space programs were closely tied to national prestige. Ocean exploration, while scientifically critical, does not always command the same visibility. This is not to say that ocean research lacks funding entirely. Many countries invest in marine science, but the scale of dedicated funding for planetary exploration has often been larger relative to mission scope. There is also a practical difference in mapping efficiency. A single orbital mission can survey an entire planetary surface repeatedly. Once in orbit, coverage accumulates rapidly. For example, radar mapping missions to Venus or the Moon produced near-global datasets within mission lifetimes. In contrast, mapping the ocean floor requires physical traversal of each region. There is no equivalent of an orbiting sonar platform that can see through water globally. Satellite altimetry provides indirect global coverage of seafloor features by measuring gravitational variations. But this method lacks the fine resolution of ship-based multi-beam sonar. Another distinction lies in accessibility after mapping. Once a planetary surface is mapped from orbit, high-resolution imagery remains available for analysis indefinitely. Researchers can examine features repeatedly without returning to the site physically. In the ocean, high-resolution mapping depends on returning ships to the region. If additional detail is needed, another expedition must be organised. Logistics also differ in scale and coordination. Launching a spacecraft is expensive, but once deployed, it operates continuously without daily crew requirements. A research vessel requires crew, fuel, supplies, and maintenance for each mission. Deep-sea vehicles must be recovered, inspected, and repaired between deployments. Time at sea is limited and expensive. There is another psychological factor. The ocean's surface is visible. We see waves and assume familiarity. Space appears distant and unknown. This perception can influence how exploration priorities are framed publicly. Yet in reality, the deep ocean is less accessible than many orbital targets. Even so, the comparison should not be overstated. In terms of human presence, space exploration has been limited as well. Only a small number of astronauts have travelled beyond low Earth orbit. Most planetary exploration is robotic, similar to deep-sea exploration relying on ROVs and AUVs. Both domains depend heavily on unmanned systems. Technological crossovers exist too. Materials developed for spacecraft can be adapted for submersibles. Autonomous navigation algorithms benefit both fields. In recent years, interest in ocean mapping has increased through initiatives such as Seabed 2030, which aims to produce a complete high-resolution map of the ocean floor. Progress is accelerating, but the starting point is large. It is not that space is easier in all respects. It is that the ocean's physical properties, water opacity, pressure, corrosion, and sheer surface area, create constraints that make global high-resolution mapping slower to achieve. Exploring space often involves looking outward with telescopes and orbiters. Exploring the ocean involves sending equipment into an environment that actively resists intrusion. Both are challenging, both require sustained investment. But when someone says that we know more about Mars than about our own ocean, what they usually mean is that we have high-resolution global imagery of Mars' surface, whereas much of the ocean floor remains mapped at lower resolution. That distinction matters. We understand the broad structure of the ocean basins. We know where the major ridges and trenches lie. We monitor surface conditions globally. But detailed, fine-scale mapping across every square kilometre of seafloor has not yet been completed. The ocean's vertical dimension adds further complexity. Even if the entire seabed were mapped in high detail, the midwater layers would still require separate biological and chemical surveys. Exploration progresses at the pace allowed by physics, engineering and funding, and while space exploration may appear to move quickly because orbiting platforms cover wide areas efficiently, ocean exploration continues methodically, one survey line and one descent at a time. From here, the focus shifts from comparison to reflection. Given the tools we have and the challenges we face, what exactly remains unknown? Not in dramatic terms, but in measurable gaps. Because beyond mapping percentages and technological explanations lies a more direct question. What specific aspects of the ocean are still not fully understood? After centuries of navigation, decades of systematic mapping, thousands of research cruises, satellite networks, autonomous floats and deep-sea vehicles, it would be easy to assume that the remaining unknowns are small details. But when you step back and look carefully, the list of unresolved questions is still long, not in the sense that the ocean is a complete mystery. We know the outlines of the basins, we understand plate tectonics, we track surface temperatures and currents in near real time. We have identified hydrothermal vents, mid-ocean ridges, abyssal plains, and trench systems. The unknowns are more specific, more granular, more distributed across layers and systems. Start with mapping resolution. While we have global bathymetric coverage at coarse resolution from satellite altimetry, a significant portion of the ocean floor has not been mapped using high-resolution multi-beam sonar. That means small-scale features, minor seamounts, narrow canyons, localized ridges may still be missing from detailed charts. We do not yet have a uniformly high-definition map of every square kilometre of seabed. This matters for geology, ecology, and hazard modelling. Submarine landslides, for example, can generate tsunamis. Understanding slope stability requires detailed terrain models. There are also biological unknowns. Estimates of how many marine species exist vary widely. Many scientists believe that a large percentage of deep-sea species remain undescribed. Each time a remotely operated vehicle surveys a previously unvisited site, new organisms are often recorded. In some regions, especially abyssal plains and trench systems, sampling density is low. Entire communities may exist that have never been observed directly. Even in more accessible midwater zones, species abundance and distribution are not fully quantified. The biomass of mesopelagic fish, for example, has been revised upward in recent years based on improved acoustic surveys. Earlier estimates underestimated their numbers. That revision alone changed understanding of global carbon cycling. Microbial diversity presents another layer of uncertainty. Genetic sequencing has revealed enormous microbial complexity in seawater and sediments. Yet many microbial lineages are known only from DNA fragments, not from cultured samples. Their metabolic functions are inferred rather than fully characterized. Understanding what these microbes do, how they process nitrogen, sulfur, carbon and trace elements, remains an active area of research. There are also physical process gaps. Deep ocean circulation is understood in principle, but small-scale mixing processes remain difficult to measure. How exactly heat and dissolved substances move between layers depends on turbulence and boundary interactions that are not fully resolved in models. Climate projections depend on these processes. Even small uncertainties can influence long-term forecasts. The Southern Ocean is a particularly important region with persistent data gaps. Harsh conditions make continuous observation difficult, yet it plays a central role in deep water formation and carbon uptake. In the Arctic, sea ice complicates satellite monitoring and in situ sampling. As ice cover changes with warming temperatures, understanding circulation and ecosystem responses becomes more urgent. Chemical processes in deep sediments also remain incompletely characterized. Subsea floor microbial communities may influence methane release. Methane hydrates, ice-like structures trapping methane within sediments, exist in certain continental margin regions. The stability of these hydrates under warming conditions is not fully understood. If destabilized, methane release could have climate implications. Quantifying that risk requires better mapping and monitoring of hydrate deposits. There are also unknowns related to biodiversity resilience. How will deep-sea ecosystems respond to increasing temperatures, acidification, and potential deep-sea mining? Many deep-sea organisms grow slowly and reproduce infrequently. Disturbances may take decades or centuries to recover. Yet baseline data for many regions are sparse. Without comprehensive surveys, it is difficult to assess change. Soundscapes of the ocean are another area of partial knowledge. We understand that anthropogenic noise is increasing. We know that marine mammals rely on acoustic communication, but long-term basin-wide monitoring of underwater sound is limited. How noise pollution affects deep-sea species that also rely on vibration and sound detection remains under investigation. Even fundamental quantities have margins of uncertainty. The total heat content of the deep ocean is estimated from available measurements and models, but continuous high-resolution data below certain depths are still expanding. Carbon sequestration rates vary regionally and seasonally. Biological pump efficiency differs across ecosystems. In some cases, what we do not know is not because we lack technology entirely, but because comprehensive coverage is expensive and time-consuming. There is also the question of rare events. Deep-sea volcanic eruptions, submarine landslides, and episodic methane releases may occur infrequently. Detecting and studying them requires either chance presence of instruments or long-term monitoring networks. We know such events happen. We do not always know their frequency or magnitude precisely. In trench systems, species diversity may be higher than currently documented. Some trenches have been visited only a few times, others not at all with modern imaging systems. Abyssal plains, which cover vast areas, are sampled at relatively few points compared to their total extent. Even if general patterns are understood, local variation may be significant. There are also human impact uncertainties. Microplastics have been found in deep-sea organisms and sediments, but the full distribution of microplastic accumulation at depth is still being mapped. Chemical pollutants transported via marine snow may accumulate in certain basins. Long-term ecological consequences are still being assessed. Fisheries in mesopelagic zones are being considered by some industries, but without complete biomass and ecosystem data, assessing sustainability is difficult. Another category of unknown lies in interaction effects. Ocean systems are interconnected. Temperature changes influence circulation. Circulation influences nutrient distribution. Nutrients influence biological productivity. Biology influences carbon sequestration. Each link is studied individually, but combined feedback loops can produce complex outcomes. Predicting those outcomes requires integrated data sets across physical, chemical, and biological domains. When people say we have explored only a small percentage of the ocean, they often refer to direct visual exploration of the seafloor. But exploration also includes continuous monitoring, biological cataloguing, chemical sampling, and process understanding. In some areas, such as surface temperature tracking, we have dense data coverage. In others, such as deep trench biodiversity or subsea floor microbial metabolism, data remains sparse. The ocean is not uniformly unknown, it is unevenly known. Certain coastal regions are intensively studied due to economic and ecological importance. Major shipping routes and continental margins are well mapped. Remote central basins receive less attention. Bridging these gaps requires coordinated international effort. Projects like Seabed 2030 aim to improve mapping coverage. Expansion of deep Argo floats extends monitoring deeper. Advances in autonomous vehicles reduce operational cost over time. Yet even with these initiatives, the scale of the ocean ensures that exploration remains ongoing rather than complete. What we still do not know is not a single mystery waiting to be solved. It is a collection of smaller uncertainties spread across layers, regions, and processes. Some unknowns will narrow steadily as data accumulate. Others may reveal new questions as technology improves. Because exploration does not simply fill blanks on a map, it often expands the map's complexity, and that leads naturally to a broader consideration. If so much remains partially known or incompletely measured, is it possible that entire ecosystems exist that we have not yet encountered directly? Not speculative in a dramatic sense, but plausible within the scale and structure of the ocean itself. That possibility frames the next step in understanding just how much of the ocean remains beyond detailed human observation. It is one thing to say that we have not mapped every square kilometre of the seafloor in high resolution. It is another to ask whether there could be entire ecosystems that have never been observed at all. That question sounds dramatic at first, but when placed in context of scale and sampling density, it becomes more practical than sensational. The ocean covers more than 70% of Earth's surface. The deep sea alone accounts for the majority of the planet's habitable volume. Even with decades of exploration, direct visual surveys have covered only a tiny fraction of that space. Sampling in the deep ocean is not continuous, it is targeted. Research vessels select sites based on specific questions: hydrothermal vents, seamount chains, continental margins, trench systems. Vehicles descend, collect data, and return. Between those sites lie vast stretches that have never been directly observed. This does not mean that scientists assume those areas are empty. It means that detailed ecological surveys have not yet been conducted there. Hydrothermal vents offer a useful example. Before 1977, no one had seen a hydrothermal vent ecosystem. The assumption was that life in the deep ocean depended entirely on organic material drifting down from surface waters. The discovery of chemosynthetic vent communities changed that understanding. It revealed that entire ecosystems could exist independently of sunlight, powered by chemical energy from Earth's interior. Since then, multiple vent systems have been discovered along mid-ocean ridges and back-arc basins. Each new vent field often hosts species not seen elsewhere. Some organisms are endemic to specific vent regions. If one major ecosystem type remained undiscovered until the late 20th century, it is reasonable to consider whether others could still exist in unexplored regions. Cold seeps provide another example. These methane-rich environments were identified after vent systems and also host chemosynthetic communities. They differ chemically and biologically from hydrothermal vents. The discovery of each new environment type expanded the known range of marine ecosystems. Seamounts illustrate another dimension. Thousands of seamounts rise from the ocean floor. Many have never been visited by submersible or sampled biologically. Because seamounts influence currents and nutrient flow, they can support unique communities. Surveys of previously unvisited seamounts frequently record new species, not necessarily entirely new phyla, but new species within known groups. The likelihood of entirely unknown higher taxonomic groups, such as a completely new phylum, existing in the deep ocean is lower than in the past. Major body plans are generally well characterized, but new species, genera, and even families remain likely discoveries in undersampled regions. Trench systems offer additional possibilities. Each trench is geographically isolated. The Hadal zone within one trench may not connect easily to another. Isolation can drive speciation. Because trench exploration has been limited to specific sites within certain trenches, it is possible that distinct communities exist elsewhere that have not yet been sampled. Abyssal plains, although seemingly uniform, cover enormous areas. Localized variations in sediment type, organic input, and microtopography could support distinct assemblages. In addition to macrofauna, microbial ecosystems add another layer. Genetic studies reveal microbial lineages in seawater and sediments that are not yet fully characterized. Some are known only from DNA sequences. Their ecological roles are inferred but not directly observed. Given the vastness of subsea floor habitats, it is plausible that unique microbial communities exist in regions not yet drilled or sampled. There are also extreme environments that are only partially explored. Under Antarctic ice shelves, large cavities of seawater exist beneath floating ice. These regions are difficult to access. Autonomous vehicles have begun to explore them, revealing life where light never penetrates. Subglacial lakes beneath Antarctic ice sheets are another frontier. While not strictly oceanic, they connect to marine systems and may host isolated microbial communities. Deep subsurface environments within oceanic crust, accessed through drilling, reveal microbial life adapted to high temperature and pressure. Each of these discoveries demonstrates that ecosystems can exist in conditions previously assumed to be marginal. However, it is important to clarify what unknown ecosystem means. It is unlikely that there are entire classes of large, highly visible organisms in the deep ocean that have escaped detection entirely in regions that have been acoustically mapped and occasionally sampled. Large organisms leave acoustic signatures, are caught in trawls, or appear in submersible footage. But localized, specialized ecosystems, particularly those associated with specific chemical conditions or isolated topography, could remain undiscovered. The ocean scale supports that possibility. Consider that even on land, new species continue to be discovered in rainforests and deep caves, despite centuries of study. The deep ocean is far less accessible than most terrestrial environments. Sampling bias plays a role. Research tends to focus on areas of interest: vent systems, coral reefs, fisheries zones. Remote, seemingly featureless plains may receive less attention. In addition, technological limits affect detection. Sonar can map terrain, but it does not reveal biological complexity. Environmental DNA sampling can indicate presence of organisms, but interpretation requires context. Camera surveys cover narrow corridors. Given these constraints, the absence of evidence is not evidence of absence. At the same time, scientific caution is necessary. The ocean is not an entirely alien realm. Its chemistry and physics are understood at broad scale. Life evolves within certain constraints. The probability of discovering entirely new biological kingdoms is low, but the probability of finding previously undocumented species, metabolic pathways, and ecological interactions remains high. In recent years, deep-sea expeditions have repeatedly identified new species of fish, invertebrates, and microbes. Even within well-studied regions, new findings occur when survey resolution increases. The question, then, is not whether there are hidden cities of giant unknown creatures. It is whether there are distinct ecological systems shaped by local conditions that have not yet been documented. Based on current sampling coverage and known variability, the answer is likely yes. The ocean is heterogeneous. Temperature gradients, chemical inputs, geological structures, and current patterns create microenvironments. Where microenvironments exist, ecological specialization follows. Some of these specialized systems may be small in spatial extent but significant scientifically. The discovery of hydrothermal vents reshaped understanding of life's energy sources. It influenced astrobiology and origin of life research. Future discoveries, even if smaller in scale, could similarly refine understanding of adaptation and resilience. Exploration continues to reveal that the ocean is not uniform. It is layered, structured, and dynamic. As mapping coverage increases and autonomous vehicles expand survey reach, the number of unexplored regions decreases incrementally. But because the total area is so vast, even a small percentage of unvisited terrain represents millions of square kilometers. It is within that remaining space that undiscovered ecosystems could still exist, not in fantasy terms, but in measurable ecological complexity waiting for systematic study. And that leads naturally to a broader perspective. The ocean has been called Earth's last great frontier, not because it is entirely unknown, but because its scale ensures that exploration remains incomplete. Understanding how much of it we have truly explored requires recognizing both the progress made and the gaps that remain. Those gaps do not represent darkness in a dramatic sense. They represent work yet to be done, and they remind us that even on a planet mapped by satellites and crossed by global networks, there are still environments beneath our feet that remain only partially observed. If you look at a modern world map, there are no blank spaces left on the surface of the continents. Every landmass has been outlined, named, divided, and measured. Satellites pass overhead constantly. Roads and cities appear in high resolution from orbit. Even remote mountain ranges have been surveyed in detail. The ocean looks similar on that map. It is coloured blue. It has names: Pacific, Atlantic, Indian, Southern, Arctic. Major currents are drawn as sweeping arrows. Trenches and ridges are marked. It appears complete. But that completeness exists mostly at the surface. Beneath that blue layer lies the majority of the planet's living space, extending downward for kilometres. And while we understand its broad structure, we have not yet examined it with the same density and familiarity as the land above sea level. Calling the ocean the last great frontier does not mean we know nothing about it. It means that, compared to other large environments on Earth, its detailed exploration remains ongoing. The surface is monitored continuously. Satellites measure sea surface temperature, wave height, chlorophyll concentration. Buoys and floats track currents and chemistry. Shipping lanes cross predictable routes. But descend a few hundred meters and coverage begins to thin. Below 1,000 meters, darkness becomes permanent. Pressure increases beyond human tolerance without specialized equipment. Direct observation depends on robotic systems lowered carefully from ships that must travel physically across the water to reach each survey area. Mapping the ocean floor at high resolution has progressed steadily, yet it is not finished. Each year, new swathes are added. Each expedition fills in more of the grid. The Seabed 2030 initiative aims to complete a full high-resolution map of the global ocean floor. That goal reflects confidence that the task is achievable, but it also acknowledges that it has not yet been accomplished. Even once the terrain is fully mapped, exploration will not end. A detailed bathymetric map shows shape, not biology. It reveals slopes and ridges, not species interactions. It outlines basins, not chemical gradients. The midwater layers remain vast three-dimensional habitats. Mesopelagic and bathypelagic zones host organisms that migrate daily, transporting carbon and nutrients. Their total biomass is still being refined as new acoustic surveys adjust previous estimates. Microbial communities operate at scales invisible to the eye. Genetic sequencing has uncovered enormous diversity, yet functional understanding continues to develop. Trench systems have been visited only a limited number of times relative to their number and distribution. Abyssal plains cover millions of square kilometers with sparse direct sampling. The frontier is not a single dramatic boundary. It is a collection of partial data sets, incomplete coverage, and evolving questions. There is also a practical reason why the ocean remains a frontier. Exploration requires physical presence. Ships must travel, equipment must descend, weather must cooperate, budgets must allow. Unlike orbiting a planet, where a single satellite can map vast areas repeatedly, ocean mapping accumulates line by line. Still, progress is real. Autonomous underwater vehicles now operate with greater efficiency than ever before. Deep-rated submersibles reach depths once thought inaccessible. Long-term observatories transmit data continuously from the seabed. International collaborations share mapping data openly. Machine learning assists in analysing sonar and genetic data sets. The pace of discovery has accelerated compared to previous centuries. At the same time, human impact is expanding. Deep-sea mining is under discussion in certain regions. Fisheries may target deeper species. Climate change alters temperature and chemistry across all layers. Exploration is no longer only about curiosity. It informs policy, conservation, and resource management. The frontier status of the ocean carries responsibility. Understanding where vulnerable ecosystems exist requires mapping them first. Protecting biodiversity depends on identifying it. Modelling climate accurately requires measuring heat and carbon storage throughout the water column. In some ways, the ocean is more familiar now than at any point in history. Mariners cross it daily with satellite navigation. Submarine cables connect continents. Global monitoring systems track storms in real time. Yet familiarity at the surface does not translate to detailed knowledge at depth. If someone asks how much of the ocean we have really explored, the answer depends on definition. If exploration means recognizing major basins and global circulation patterns, then we have explored a great deal. If it means having high-resolution maps of every square kilometre of seafloor, then the work is still underway. If it means having catalogued every species in the deep ocean, then we are far from complete. If it means understanding every microbial pathway influencing climate, that too remains in progress. The ocean scale ensures that exploration is a process, not a milestone. Each new dataset reduces uncertainty in one area and often reveals complexity in another. The deep sea is not static. It changes slowly, but it changes. Sediments shift, currents vary, ecosystems respond to temperature and chemistry. Exploration, therefore, is not something that will ever be finished in a final sense. It is continuous observation and refinement. What makes the ocean feel like a frontier is not ignorance. It is proportion. The proportion of detailed, direct observation relative to total area and volume remains small compared to terrestrial environments. There are still seamounts never visited by camera, still trench sections never surveyed closely, still microbial communities identified only through fragments of DNA, and yet the outline is known. The global system is understood in principle. We are not standing at the shoreline wondering whether the ocean has a bottom. We know it does. We know how deep it can be. We know that life exists there. What remains is depth of detail. The last great frontier is not a blank space waiting to be discovered in a single dramatic expedition. It is a vast environment being mapped, sampled, and analysed piece by piece. Progress will continue through coordinated effort. Ships at sea, satellites overhead, autonomous vehicles below, laboratories processing samples, models integrating data. The frontier narrows slowly, but it does not vanish, because the ocean is not only large, it is layered, dynamic, and interconnected with every aspect of planetary life. And as long as there are layers not yet measured at fine scale, species not yet described, and processes not yet fully quantified, exploration continues. Not as a race to plant a flag, but a steady expansion of knowledge across a domain that covers most of the planet we live on.